So your slides will be brought up for you, but we'll just come out of this, I think. It's not going to end that straight, no. That's one. There we go. There we go.
And so what do I do to...
it's just forward and back.
Here, so that it starts.
I mean, this one, yeah. Obviously, we will go up to a full presentation. Would
And
you
then-
like me to put it up there?
Do we have a...
You'll see it like that. That's what
I
we
see.
have.
And it'll come up with that.
It'll come up on the sign, yeah. So then you...
Okay. Good.
What you're expecting.
It is, yes.
Yes.
I've got an updated version that has that corrected. You can't correct that, can you?
Yeah, sure.
It should be 1949, the second one. Stan wasn't that old. Oh, good. Well done. Thank you. Thank you. So everything's perfect then. Thank you very much.
No. Yeah, beat me to it.
Just seeing how much space there was for notes. Can I pull this out?
Probably.
Yes, yeah. Because I have done this before now. Actually, put my notes on here, switched it off, or put somebody else's presentation.
Good morning, everybody. Perhaps we can get started with this symposium. I am Ian Walmsley. It's my privilege to be the Provost of Imperial College London, and on behalf of the college, I'd like to welcome you all today for this celebration of Stan Peart's life and accomplishments. It's fantastic that we're able to have this back in 3 dimensions and to see so many people both in person here and online. And this new hybrid world, I know, is something we'll have to get used to, though those of you in the room don't need to unmute yourself before you ask a question. Now, today's event is an opportunity to honor and celebrate the life of Sir Stanley Peart, Stan as he was known, and the remarkable scientific contributions he made to the understanding of the nervous system. You'll hear much more about the details of what he did during his career and his accomplishments from colleagues who are much more expert than I in the fields that he helped to pioneer. But just to note that Stan was a scholar at St. Mary's Medical School at a time which preceded the amalgamation of the school and Imperial College. But I hope that we still at the college, through the medical faculty and its connections to the other faculties, are able to live up to his legacy. He embodied the ethos of the college, I think, discovering new knowledge and improving the world through that increased understanding. By means of the research he undertook, the education he provided, and the translation of that into the clinic. He was, by all accounts, a remarkable man, accomplished in all of these areas, a scientific leader, a caring mentor and a teacher, and a sympathetic and brilliant clinician, as well as a generous community-minded individual. Aside from all his roles just described, he took up important positions in the Wellcome Trust and the Medical Research Council, and was indeed Vice President of the Royal Society, where we are today, and, of course, was knighted for his contributions to medicine. So I'm very pleased that we have the opportunity to celebrate his life, and that we are joined today by some members of Stan's family, Celia, his daughter, Sarah, here his granddaughter, and Joseph, his grandson, who's online, I believe, as well as his former research fellows and his colleagues. And I look forward to hearing more about what he has done and to hear from you about what a great individual he was. Thank you. Let me now hand over to David for the proceedings.
Ian, thank you. That's been a very helpful introduction, and I think you've left your glasses behind.
That's why I need them.
I'm David Gordon. I'm delighted to be here. I have many thank yous I could offer. I'll do them mostly later in the day, but just 2 now. One is to thank Celia and the rest of Stan's family for suggesting that we should have a day like this. And I think it's been a very interesting exercise to develop it. It's put a few grey hairs on me and Peter Sever over the last few months, but you know, it's been very well worth it. I think the other thank you is to all of you for being here, but also everybody out there who's watching at a distance. And I'll only mention 2. One is we know that Joe Pett, Stan's grandson, is watching out in Zambia. And we know that some of the alumni of the medical unit are actually watching in Sydney, New South Wales. So we've managed to get round the world. So thank you all very much for coming. One other person who's watching at a distance we should mention is Katie Livingston, who was the person who worked with us with the details of getting the meeting together. And she was unfortunately a contact of the disease just a day or 2 ago, so she's had to isolate. But Katie, you are watching, and thank you very much. Now, when we put the programme together, we obviously had to think through the entire scientific career. And of course, there is no one around now who was working in the same field as Stan in exactly the same way as he was right at the start of his career, pretty well 70 years ago. So we need a real historian to take us through that. So I'm delighted to introduce Tilly Tansey, who is Professor of Medical History and is going to talk about the early discoveries in Edinburgh, at Mill Hill, and all those other things that came along. Tilly.
Thank you very much, David. I would like to begin with my thanks and to thank the organisers for inviting me to this conference because, as David's probably just stressed, I'm the only speaker here who didn't actually work with Stan. I first met him in 1986 when I was a research physiologist interested in medical history and about to start a history PhD on Henry Dale. Stan was always incredibly helpful and interested in my work, and he remained so for the rest of his life. He was elected to Fellowship of the Royal Society in 1969, proposed by Sir John Gadam, and I'm very grateful to the librarian of the Royal Society for allowing me to see this document. The nomination for Stan's work refers to a wide range of work on noradrenaline, angiotensin, 5-HT, the development of sensitive bioassays for bioactive molecules, especially renin and angiotensin, and investigations into their roles in health and disease. So not too surprising then that his candidature was supported by eminent clinicians such as Sir John McMichael here, second from the bottom, and Sir George Pickering, who seconded the proposal. But it was also very strongly supported by physiologists and pharmacologists, including Heinz Schild, Mary Pickford, Charles Harrington, Arnold Burgeon, and Hugo Huggett. But the five supporters, 5 names on our list, I'd like to mention in particular. Harold Byrne. In the middle, John Gadam. Far right here, Wilhelm Felberg, G.L. Brown, and Martha Vogt. All supporters of Stan's election, and they had one major thing in common. They had all worked at various times and in various capacities with Sir Henry Dale, either at the Wellcome Physiological Research Laboratories or the National Institute of Medical Research, then in Hampstead. And they were enormously influenced by Dale in his approach to science and in his work. Dale was president of the Royal Society during the Second World War, and this rather poor reproduction is of a portrait here of him as president of the Royal Society. For many years, it has been on the staircase just behind the registration desk for today's meeting. During the lockdown, the Royal Society has taken advantage of nobody being here to move the portraits around. So it's no longer there, but I have located it. It is in the dining room just to the left of the door, and I believe you can, if you want to look at the original portrait by James Gunn, go and have a look at it. Henry Dale had shared the Nobel Prize for Physiology or Medicine in 1936 for the elucidation of chemical neurotransmission, especially the role of acetylcholine in the parasympathetic nervous system and at the neuromuscular junction. However, characterizing the neurotransmitter of the sympathetic nervous system was proving difficult, although it was known to resemble adrenaline. Indeed, as early as 1910, Henry Dale had, with a chemist colleague, George Barger, working in the Wellcome Labs, had identified a range of chemicals similar to adrenaline. And Henry Dale coined this wonderful, useful word, sympathomimetic, to describe their activity, i.e. the ability to mimic sympathetic stimulation. Of all the chemicals he and Barger examined, they announced that noradrenaline was an exact match for sympathetic stimulation. But noradrenaline wasn't known to occur naturally. It was merely a synthetic novelty that Barger had made in the lab. The search for that elusive sympathetic neurotransmitter continued for many, many years, and the catch-all name sympathin was given to it to disguise or to encourage the fact that the precise chemical identification had not been made. By the late 1940s, the professor of medicine at St Mary's, George Pickering, shown on the left here, his research interest was predominantly in hypertension. And he was following the current research then in sympathetic activity with particular interest. He suggested to his young houseman, Stan Peart, that he might be interested in doing some research in the area. Although Pickering wrote him an open letter of recommendation, which you can see here on the right, he also suggested to Stan that he would benefit from working with a real scientist like John Gaddam. And so Pickering also contacted John Gaddam, who was then Professor of Pharmacology in Edinburgh, and suggested that he might take on this young man for a year, and Pickering also supported Stan in getting an MRC studentship for that year in Edinburgh. And thus, Stan arrived in Edinburgh, without never even having met Gaddam before, to embark on work from which two landmark publications appeared. The first was a paper by Gaddam and Peart with Martha Vogt. They devised and assessed over 20 different chemical and bioassay systems to establish 5 sensitive bioassays, quantitative bioassays, that were then used in parallel to measure adrenaline-like substances. And Stan produced a single author paper on an entirely new method for stimulating the release of sympathin from the spleen of the anaesthetized cat. And he also clearly identified, using those 5 assays that the previous paper had delineated, he clearly demonstrated that the chemical released when the splenic nerve was stimulated was noradrenaline. This was a major discovery, a landmark paper in the history of neurotransmission, and it impressed a number of visitors to Gaddam's lab, in particular one, the Swedish pharmacologist Sven von Euler, who won the Nobel Prize in 1970 for his own work on the role of noradrenaline in the sympathetic nervous system. Now, both of these papers include an astonishing amount of work, and some rare laboratory notebooks from this period have been shown and emphasize the numerous amounts and numbers of experiments they all undertook. This is one of John Gaddam's notebooks. It's recording experiments from 1942 to 1952, his period in Edinburgh, and it's very helpfully indexed, as you can see here. So it's on the bottom left here, there's a short index, so it is easy to just look at the sympathin experiments rather than plough through the whole book. And there's another notebook. This is actually Stan's notebook from this period. It's in the possession of his daughter, and I'm very grateful to Celia for allowing me to look at this and other material in her possession. Stan actually struggled a great deal during his year in Edinburgh, as he recalled in an interview in 1994. That's when I really had to learn the basic pharmacology, he said. To me, at that time, pharmacology was, as it is to most medical students, not something they took very seriously. It didn't loom large in the medical curriculum, and I was actually taught how to make pills in the pharmacy course. He continued, "It was a really tough year. I couldn't get the preparation, and this was the standard preparation in Gaddam's lab of using the perfused liver of the cat. I couldn't get the preparation to work properly. I was pretty desperate, you know, and was pretty close to feeling that I was completely incompetent. Gaddam said to me, 'You're not doing very well with this, are you?' But eventually Stan began to improve in the lab, and in his interview, he thanks Martha Vogt in particular for helping him both with the theory and the practice. And as Stan improved, Gaddam arranged with the MRC for him to have a second year in Edinburgh. But Stan's problems remained with that main research preparation, the perfused cat liver. return to Stan's interview. I decided I'm not going to persist with the liver. It's killing me. Why don't I try the spleen? And lo and behold, as soon as I did that, I started to get results. You know, they just started to flow. And flow they did. He clearly demonstrated that the blood collected from the cat's spleen during stimulation of the sympathetic nervous system, the splenic nerve, contained noradrenaline. The first time the substance released by adrenergic nerves was clearly identified by tests that unambiguously identified noradrenaline. And also among Celia's collection is this rather poignant reprint of that first paper. It's Stan's paper, proudly inscribed to his parents. In 1948, Stan was called up into the RAF, and in 1950, he returned to the medical unit at St Mary's, where he became deeply involved in hypertension research spearheaded by Pickering. Pickering was convinced of the importance of identifying the components of what we now call the renin-angiotensin-aldosterone system of the kidney. Peart started to work on this system, and he extracted a crude extract from a rabbit kidney of what was then named hypertensin, now known as angiotensin. But he could get no further in the labs available to him at St Mary's. Once again, Pickering suggested that his young acolyte should devote more time to research and try to purify and identify the chemical composition of his extract. And thus, Stan was sent to the NIMR at Mill Hill. This was then a very new building. It was opened in 1950. The old NIMR transferred there from Hampstead into newly equipped labs. And, to quote from the opening booklet, it included state-of-the-art facilities such as electron microscopy, electrophoresis, high-speed centrifugation, ultrasonics, radioisotopes, and mass spectrometry. Now, you might think that Stan would go to the pharmacology lab at NIMR, which is where Gadam and Vogt had both worked in the past. But Pickering consulted the NIMR director, Sir Charles Harrington, shown on the far left. He was a distinguished biochemist who had just isolated thyroxine. And Harrington recommended that Stan should join the physical chemistry department, the lab of Archer Martin, shown in the middle there. And Martin had just won the Nobel Prize in chemistry for his development of separation techniques, in particular the development of partition chromatography. In turn, Martin suggested that Stan should work with Rodney Porter, shown there top right, and Porter was to win his Nobel Prize in physiology or medicine in 1972 for the chemical structure of immunoglobulin. Stan recalled in that interview in 1994, Stan recalled that as with his arrival in Gadam's lab, he was initially completely overwhelmed by Porter's lab and its technical demands. As he said, Porter had views on doctors that were somewhat scathing, actually. He didn't trust them an inch, very wisely, I think. I came and occupied the bench closest to the window and introduced a rat into the place, with rather nice gamma globulin work going on at one bench as far away from me as possible. And there was I, putting up this rat for bioassay of the blood pressure-raising properties of the material I was interested in. But Rod got used to it. As in Edinburgh, he had a slow start, learning the necessary technical skills. He learned separation skills such as reverse phase chromatography, gel electrophoresis, and spectrophotometry. But once he had mastered them, a stream of papers appeared. These are just the titles of papers in Biochemical Journal and in Nature. Some were single author, some with the biochemist Don Elliott, finally isolating a pure, biologically active extract and characterizing the amino acid sequence of what we know as angiotensin. Now, throughout his time at Mill Hill, Stan was actually employed by the medical unit at St Mary's. His one obligation there being to teach medical students on a Thursday afternoon. By 1954, Pickering suggested that perhaps Stan should or could spend more time than one afternoon a week at St Mary's, And he willingly returned to full-time clinical work, although admitting that initially he was a dangerous doctor, having been away from clinical medicine for so long. The story of his career at St Mary's is, of course, going to be continued by Peter. But I would just like to return, my final slide, to the first one, Stan's Royal Society Election Certificate. Now, this was written in 1964, when he was first proposed by John Gaddam. And so much more was to come, which the rest of today's speakers are going to elucidate. As Pickering noted in his letter of recommendation in 1946, his ability and his energy should make him do great things. I believe he did. Thank you.
Tilly, thank you. And a fascinating piece of history. I think we could talk about that, or you and I could talk about that for hours, and indeed have done. But our next speaker is Peter Sever, who's going to talk about Stan and the legacy in the St Mary's years after he went back from Mill Hill.
Thanks very much, David, Cecilia, Robert, friends, colleagues. Stanley Peart was a giant of a man. As the Provost has said in his introduction, he was a scientist of international fame. He was a mentor to dozens of young researchers and clinicians. He was a unique teacher of students of medicine. And above all, he was without doubt the finest clinician that I have encountered in over 50 years of practicing medicine. Now, we've heard from Tilly about his early years in science in Edinburgh and at Mill Hill. I'm going to focus on the period which he was Professor of Medicine at St Mary's, appointed in 1956 on the occasion that George Pickering moved to Oxford to the Regius Chair. Now this is if you like, a summary of my perception of the Peart legacy. And I've shown on this slide, on the right-hand side and in the brown boxes, a very large number of contemporaries of mine who spent their formative research years on the medical unit at Mary's. Many of them are here today, I'm delighted to see, and they will be telling their own story. I'm going to focus on the names on the left in the blue boxes, starting with some early Mary's graduates who moved on to the unit, Brown, Robertson, Lever, and Graham Smith. And then to spend a little time talking about the itinerants, those individuals from far afield, Australia, North America, and Europe, who spent varying amounts of time on the unit, but contributed enormously to the work of the unit under Stan's guidance, and who returned to their countries of origin to occupy senior academic posts. Now, we can't really talk about Stan and the unit without at least some introduction to the renin-angiotensin system, and I apologize to those of you who probably know much more about the system than I do, but for those of you who don't, this is a very quick whistle-top tour. It kicks off with the enzyme renin released from the kidney in response to various stimuli. It acts on a hepatic protein, angiotensinogen, to form the decapeptide angiotensin 1. This is then converted by angiotensin-converting enzyme present in the lung and in the vascular endothelium to form the active substance angiotensin 2. This is a potent vasoconstrictor of blood vessels and therefore influences blood pressure. And it also importantly acts on the adrenal gland to cause release of the mineralocorticoid aldosterone. Now, the system is vitally important as a key regulator of salt and water homeostasis, and it's also involved in the pathophysiology of a number of cardiovascular and renal diseases. It's a very old system. Components of the renin system have been identified more than 500 million years ago. It was present, or components were present in chordates, in primitive vertebrates. It was vitally important in the migration of species from water to land. And of course, in the last 18 months or so, there's been a huge focus on one component of the renin system, and that is angiotensin converting enzyme 2, which is present in the lung and elsewhere, but is the binding site for the spike protein of SARS viruses. And it is the complex formed by this binding that is internalized and leads to infection with coronavirus. Now, what alarmed many of us when this was discovered was that there are a huge number of people out there on drugs which inhibit the renin system and which have the potential to upregulate ACE2, which could conceivably increase the risk of infection to people who are on these drugs and perhaps increase the severity. Now, fortunately, a number of observational studies have been done over the past year, including one that we've just completed in collaboration with the University of Cambridge and based on UK Biobank data, which suggests that far from increasing the risk of coronavirus infection, if you're on an ACE inhibitor or an angiotensin receptor blocker, you're probably slightly protected, at least from the severity of infection. Now back to Stan and his challenges when he took over command of the unit in the mid-1950s. As we've heard from Tilly, he had discovered the structure of angiotensin 2, and the challenges then were to find out, well, precisely what did angiotensin do, what were its actions, which tissues did it act upon, how did you measure it, how did you measure other components of the system, such as renin, what was the relationship between different components of the system, renin, aldo, and sodium, to investigate the role of renin in the phenomenon associated with renal artery stenosis. And for those of you who are not familiar, that is a severe hypertensive condition brought about when there is narrowing of one or more of the renal arteries, in which it is believed that there is stimulation of renin and that this might be causally related to the subsequent hypertension. And then finally, in his last few years, to study at a cellular level the mechanisms involved in renin release. So these were the challenges that the young research fellows were tasked with when they arrived on the unit. And the first three I'm going to draw to your attention, the famous Glasgow triumvirate of Joyda Brown, Bob Robertson, and Tony Lever. These were three Mary's graduates in the 1950s who, after their house jobs and early clinical jobs, all joined the unit much at the same time and were set the tasks that I showed on the previous slide. They were prodigious researchers. They wrote huge numbers of papers. They published up to 6 papers in The Lancet alone in 1963, and 4 of them are shown on this slide. Their reputation grew rapidly, and in the mid-1960s and 1965, the MRC invited all 3 of them to set up a new blood pressure unit in Glasgow, and that unit in itself then became internationally established, and they themselves trained large numbers of hypertension specialists, nephrologists, and so on, who went on to become world leaders in the field. The next Mary's graduate was David Graham Smith. He had done a PhD with Albert Neuberger in the Department of Clinical Biochemistry at Mary's. He'd studied the biosynthesis of serotonin, and Stan was very interested in serotonin because it was synthesized by and released by a rare gastrointestinal tumor, the carcinoid tumor. And he and David spent many months and years researching and studying these patients, and they became world authorities in the field. David went on to expand his interest in biogenic amines in relation to psychotropic drugs, and he was appointed to the chair of clinical pharmacology in Oxford in 1971. The next group of patients, the next group of people are the The Australians, there were many. I've highlighted 4 on this slide. I'll begin with Graham Boyd. Graham Boyd had a brilliant mind, and he was one of the key scientists in the lab who discovered the initial method for measuring renin activity. As the years went by, he became perhaps less of a scientist and more of a philosopher, and a degree of eccentricity became more and more evident. He produced an extraordinary monograph I show at the top right there, entitled Stress, Disease and Evolution, in which he came to a number of startling conclusions, not least was that sympathetic activation under the influence of stress was involved not only in cardiovascular diseases and cancer pathogenesis, but also in evolutionary mechanisms through ischemic destabilization of the genome. Far-fetched indeed, but that was our Graham. Anyhow, he returned to Tasmania as Professor of Medicine. He was revered by generations of Tasmanian medical students as an inspirational teacher. The second Australian, Graham Boyd, and I believe Graham is with us today on the internet. He was also on the unit at the time that I joined it. He was yet again a worker on the renin-angiotensin system. He had focused in some of his studies on vasoconstrictor nucleotides released from the kidney. He expanded his interest. He returned to Sydney as Professor of Medicine and Nephrology and was involved, for example, in some of the Australian clinical trials in hypertension. Bob van Dongen was a Dutchman who spent much time at Mary's before moving to Australia, where he worked with Laurie Bailyn in Perth. He was appointed as Professor of Clinical Pharmacology. He diversified his interest in hypertension, published extensively, but sadly died prematurely of leukemia in 1963. And another individual, another Australian who unfortunately died early was John Shaw. He had spent time investigating gastrointestinal mechanisms involved in sodium regulation, and he returned as Professor of Clinical Pharmacology in Sydney, but I'm afraid I know a little more about his work when he was back in Australia. We didn't have many North Americans, but I highlight 2 here. Sandy Logan was from Montreal originally. He was a contemporary of mine on the unit. He was part of the renin-angiotensin researchers. He developed more widespread specialist interest in hypertension on return to Toronto as Professor of Medicine, and he was very much involved in developing the Canadian hypertension guidelines. Bob Carey was at Mary's before my time. He was an endocrinologist by background and subsequently returned to the University of Virginia as Professor of Clinical Endocrinology, and he had a number of widespread interests, particularly in adrenal causes of hypertension. The Europeans, they mainly came from Italy, and this may have been partly because of Stan's links with Italy. Alberto Zanchetti, one of his contemporaries in the early days of hypertension research in Europe. There are 3 names here. Pino Bianchi was also on the unit before my time. He was a brilliant man, and one of his remarkable discoveries was as a result of studies on genetic models of hypertension in animals, in which he showed that if you transplanted the kidney from a hypertensive animal to a normotensive animal, the normotensive animal became hypertensive. And that was really one of the first clues that the site of the key abnormalities, perhaps in many patients with hypertension, was in the kidney. Achille Pacina spent a lot of time on the unit, involved with colleagues working on the renin system. He returned to the University of Padua as Professor of Medicine. And lastly, but not least, Joe Saniella. Now, there are some apologies for putting him on this slide. He has Italian heritage. I think he was born in this country. But he worked with Stan for a long time and was probably Stan's last PhD student, working on the isolation of renin granules from the kidney. Now, I diversify for a moment, if I'm allowed. I was the first heretic to move away from the renin system. I thought the field was crowded. And in my sort of young research days and naivety, I didn't think the renin system had got much to do with hypertension. So I wanted something else to study. And I was quite impressed by new technology that was being developed around the world using highly sensitive techniques to measure the neurotransmitter noradrenaline spilling over from nerve endings into the bloodstream. Now, Stan wasn't very impressed with this. He'd written a review in Pharmacological Reviews on catecholamines in hypertension, in which he said there was no evidence for increased catecholamines in hypertension, and therefore the sympathetic nervous system wasn't really to be further considered. But of course, what was obvious, that the technology for measuring catecholamines in those days was incredibly crude. And now with novel techniques to measure these tiny amounts of neurotransmitters spilling over into the bloodstream, it was time to look afresh at the situation. And to cut a long story short, we and others published what were then quite large series of studies, controlled studies in hypertensive individuals, and suggested that certainly in the younger patients there was evidence of increased noradrenaline spillover into the circulation, perhaps indicative that the sympathetic was playing a role in some people early on in the pathogenesis of the disease. Now, for me, the whole story became much more interesting as a consequence of some really quite different studies that I was initially involved in Southern Africa, looking at blood pressure changes from tribal people moving from rural environments into urban environments. Now, this whole story is going to be developed by Neil Poulter later today. But in the early studies, it was quite obvious that in association with the blood pressure rise in the urbanized Africans, there was a huge increase in dietary sodium. Now, was there a question, or was it a possibility that you could actually link these two hypotheses? And the problem with the thinking about hypertension in those days was that people were very sort of monocular. You know, there had to be a single unifying cause, which was intrinsically wrong. That was bound to be wrong. And so we had the idea that perhaps there were two environmental influences that were initiating the blood pressure rise, and they are summarized in a very simplistic form on this slide. Normally, if you load someone with salt, the body's pretty efficient and it persuades the kidney to get rid of it, and that's largely due to the stimulation of negative feedback mechanisms that tell the kidney to get rid of the sodium. On the other hand, if at the time you're loading the individual or experimental animals with salt, you stress them, then the brain takes over. It overrides the negative feedback mechanisms. The kidney is then told to retain the salt. You get a volume-dependent rise in blood pressure, and that's the beginning of hypertension, however we define it. So it was a dual environmental hypothesis. It has its basis in sound experimental studies, and there are some quite elegant studies in man that support it. So we published the hypothesis in 1989, and to my knowledge, nobody has ever specifically disproved it. Now, I was very excited about this, and so I thought was George Pickering. Because George, when he was at Oxford, used to come to Mary's about once a term when he attended the medical school council meetings. And I suppose for old time's sake, he'd wander up the stairs to the old medical unit lab, and he'd come and chat to me about my research. And I was extremely flattered by this, as it happened on several occasions, and this was much to the consternation of most of my colleagues that were working in the lab, whom he studiously ignored, until one day, and I'm sure it was you, David, that pointed out to me, he said, "You know, Peter," he said, "it's not your research that George is interested in, it's your attractive Polish technician who always provides me with a cup of tea." So that is my very, very brief sojourn around my perception of the Peart legacy, a very large number of people who benefited from his leadership and who went on to do great things in great places around the world. Now, I can't finish without mentioning all the clinicians. Many of these passed through the unit, and their subsequent careers as consultants within the NHS were surely influenced by Stan's leadership in their early clinical training days. So I conclude by saying that Stan Peart was, in my view, the last real professor of medicine. He will be remembered for being a scientist, a teacher, a mentor, a clinician, and for all those bow ties, lovingly made by Peggy, and of course, the Red Sox. Thank you very much.
Peter, thank you. I'm sorry about the bow tie, but I haven't got Red Sox. We have 5 minutes for questions. We even have a facility for questions from people listening at a distance. There just might be one from Sydney, because when you went on to talk about Graham MacDonald, you referred to him as Graham Boyd. Sorry, Graham. Any questions, please? Or have we left you in stunned silence? Please. Could you please introduce yourself as well?
Stephen Williams, formerly University of Manchester, but Stan Peart was a Master at the Hunterian Institute when David Gadget and I were working there. I'd just be interested to hear more about what Sir Stan did when he was working in Fleming's lab.
Fleming's lab.
I don't, history. I don't know an awful lot about that period. He does talk about it in his recorded interview in 1994. Again, I think it was Pickering who said, well, why don't you go and see how lab science works? He was, the discussion in the interview is actually more about credit, because, of course, there's a lot of debate about Fleming and Florey and who should have the credit for penicillin. Stan was very clear that Fleming was actually undervalued. He actually thought he was a very great man. He thought he was very modest, but he thought that actually he had very clear ideas and was a good technical worker. He said Stan learned basic microbiological techniques there. He said it was always stood him in good stead that he learned to pull pipettes. But he doesn't say a great deal about it. It was just an experience in the lab of a great man. Not just an experience, but he doesn't say a great deal about it in terms of his own scientific development.
I actually do think there's one very particular thing, though, that Stan, of all the people I've ever seen, was the best at working on a really obscure infectious disease. He could just, his diagnostic skill there was terrific. Steve?
It's just I have a personal interest because my mother was a lab technician in Fleming's lab after the war. So I do wonder whether they overlapped, but I think probably not.
So I can't hear.
Yes. Sorry, just saying that Steve Williams' mother was a lab technician in Fleming's laboratory.
Oh, right. I'd love to talk to you. I'm particularly interested in lab technicians. I've got hundreds of hours of interviews with lab technicians, particularly at the NIMR. So yes, I'd love to talk to you about that, please.
Any more questions at all? Yes, we have one at a distance.
Yes, I think we've got a couple of questions from the live stream. Firstly, Isato Sa asks, is there a tool for the pharmacokinetic and pharmacodynamic profiling of drugs acting on the renin-angiotensin system?
Masks. I can't hear what he said. Do you think you could drop your mask so we can hear what you say?
Sorry, yeah. Okay, it's a lot of complicated words in this question. Okay, so is there a tool for the pharmacokinetic and pharmacodynamic profiling of drugs acting on the renin-angiotensin system?
Is there a pharmacokinetic, pharmacodynamic
tool for investigating the mechanism of drugs acting on the renin-angiotensin system?
I don't think there are any specific tools. I mean, the science of pharmacokinetics and the science of pharmacodynamics are now, fairly well established, and many of those principles were applied in the early days when people were infusing angiotensin, and investigating its duration of action, its mechanism of action, its metabolism and distribution and so on. And those are essentially the same techniques that were used then that are used today.
And there is another question from the live stream.
We've got a couple of questions from the same person. I'll just ask maybe one more. With the predictive value of angiotensin posing challenges for drug doses, what are the approaches for determining the dose-response relationships?
I didn't hear that either.
Sorry, could you repeat that again?
Of course. Sorry. With the predictive value of angiotensin posing challenges for drug doses, what are the approaches for determining the dose-response relationship?
The predictive value for angiotensin for determining drug doses. I think that's a question we'd need to take in writing at another time.
Okay.
Yeah, I mean, it's not used as a drug. I mean, there's a lot of work on inhibitors of angiotensin too, but not. It's used. I suppose it was used occasionally as a stimulant.
Yes. Yeah.
In patients, largely in clinical research.
Good. Thank you. I think we'd better move on. Thank you both very much. And the next speaker is my old friend Chris Wilcox, who is currently in Georgetown. My slight worry is I can't see where he is in the room. There he is. Chris, over to you.
Good morning, everybody. It's lovely to be here, see some old friends and some faces I don't really recognize, to be quite frank, because I've been abroad in America for 40 years or so, and here I am meeting some of you again for the first time in that long period. Thank you, Peter and David, for your persistence in getting this meeting together, despite all the difficulties. And I'm delighted and honored to be invited to participate. So I've been asked to talk about Stan, the renal physiologist. I'm going to expand a little bit to the physiologist and use this as an introduction, because one of the things I learned when I prepared for this talk and looked up Peart WS in PubMed is what an extraordinarily prolific career he really had. I mean, I think everybody was well aware of his contributions in the field of renin and angiotensin, but they spread so much further. Tilly outlined some of them, and you're going to hear a lot more about them later. So my talk, in a sense, I think, will be an introduction to much of what comes. I wanted to touch the highlights of his career, so that we can all remember them together and revere them, frankly, and then to delve a little bit further into one or two of them and remind you what he actually discovered. One of the special things about Stan was he was a great basic scientist, no question. Very original, brought new techniques to the field, new discoveries, new insights. But he wasn't satisfied with that. Most scientists would have been more than satisfied to have discovered these very important biological principles, as you heard from Tilly. He wanted to translate those himself into whole human physiology or medicine. So as I go through these, I'm going to try and remind you of the basic discoveries and how he himself took the step of doing the translation. Most unusual. Most basic scientists leave it for somebody else to do the translation. But Stan wasn't happy unless he took it all the way through to man. It was only then that he knew that it was a worthwhile discovery and not just a lab event. So, as you heard, I wasn't fully aware, actually, of his brilliant contributions to the catecholamine field and his early study in which he stimulated the sympathetic nerves to the dog kidney and showed that the principle released was not adrenaline as had been thought, or as Burns had claimed, acetylcholine, but it was actually norepinephrine. Very important finding that really set the field going, and I'm sure was very influential to Peter and his studies. But he did, on the other hand, in that paper that was referred to with Gadam and Martha Voigt, show that the circulating catecholamine was adrenaline, or included adrenaline. And in this paper, he not only showed that and showed how to isolate it, but he also showed what the actions were in experimental animals. So some of the translations from that was the use of noradrenaline and adrenaline excretion to diagnose pheochromocytoma in 5 patients, a huge step forward. And I just bring your attention to the work that he did on clonidine with Chris Mathias. He showed that clonidine fails to lower blood pressure or norepinephrine in patients with pheochromocytoma. And this was actually some of the work that he did there. And you'll see on the left blood pressure before and after clonidine, not changing in the patients with pheochromocytoma, but falling pretty dramatically in essential hypertension. And the huge levels of norepinephrine uninfluenced by clonidine in the pheo patients, but falling in the normals. And the reason I wanted to show you this is many of you will have used the clonidine suppression test in the clinic to diagnose pheochromocytoma. And here it is for you, beautifully displayed by Stan and Chris Mathias and colleagues. But he was not one to blow his own horn. He didn't actually propose this, to my knowledge, as a test for pheochromocytoma. Others came later and used the data to that end. He had massive discoveries in the field of angiotensin and renin, which have already been referred to, the proper isolation and characterization of hypertension, without which we couldn't really have made big advances in the field, and its sequencing, a terrific feat as so long ago, is isolation of pure renin from the pig kidney, which was a very important step in one of his quests, which is to understand better what are the actual mechanisms for renin release from the kidney. And Joe Sangiella made much use of this, because it was only if you had purified renin that you could really make such studies and think about what dissociated renin from the granules. He also showed with Tony Lever that renin and angiotensin was released into the lymph. And that was a terrific study, because it showed us that renin and angiotensin are very important local processes within the kidney, not just systemic hormones. And indeed, we now know that there are a number of situations in which angiotensin and renin levels in the kidney increase and yet decrease in the circulation. They don't just follow each other in a passive way. And it was this discovery which led to ways to investigate that, as well as the calcium dependency. So here's from that early study with Tony Lever, and he shows here the huge levels of angiotensin that he got from cannulated lymphatics coming from the dog kidney, and angiotensin and renin. And we took this on, as I'll show you later, and did a lot of work on renin, because it gives you insight into the interstitial environment of the kidney in a unique way. And Stan and Tony Lever recognized this long ago and produced this nice evidence here. With Bob van Dongen here, he shows the critical role of calcium in renin release using an isolated rat kidney. And notice that it's the inverse of what would be anticipated from all of endocrinology up to this point, that it's low calcium that stimulates renin and high calcium that inhibits it. And this was really the challenge for Joe Sanghela, to understand how calcium actually interacted with the granules and regulated release of renin from the kidney. So what were the translations of some of these work? Well, there were many, of course, really huge translations in the field of hypertension, but some of the most direct that those of us on the medical unit will remember is the diagnosis and treatment of renal artery stenosis. And we probably remember the bilateral ureteric cannulation studies that we so hated on the unit, because the patient would come back from the radiology department. Often one of the ureteric cannulae had fallen out on the way, or the radiologist had forgotten to mark which was the left and which was the right. So it was a whole day's work to infuse PAH and to get the individual kidney function that Stan always wanted before he would really make the diagnosis of unilateral functional renal artery stenosis or renovascular hypertension. But there it was, and it was a great contribution which others went on later to exemplify. He made big contributions in a new field, really, which is the communication between organs. Up until really when he was getting into this field, physiology was about the individual function of each organ. And so you could study an organ in isolation, isolated and perfused. That gave you physiology. Not for Stan. He saw the organ as being part of the environment of the whole body. And that a lot of the understanding that we had to have if we were really going to see how that organ worked was how it communicated with other organs in the body in an integrated manner. And the work that first David did on the gut, how the gut communicates to the kidney after a salt intake, which is now really taken off with the microbiome and the recognition of IL-17 affecting cerebral function on the one hand, and some of the lovely work that Robert Unwin did on the other, that gut-derived hormones directly influence renal function. Those were terrific findings that Stan made with some of his best students who are here today. Also very practical ones. He studied the output of salt from an ileostomy and showed that it's really an unregulated salt leak. Very important clinical finding that I've encountered several times, where patients with ileostomies will come in very salt depleted, no salt in the urine, and people will wonder what's going on. The salt is not in the urine, it's in the ileostomy bag. And it's not regulated by salt in the diet, unlike the kidney. It goes on and on regardless of the body's needs. Lovely studies. And then you might wonder why I talk about Pindolol, a drug you've all forgotten. Well, Stan used to like to go skiing, and he'd go to the Alps every summer, care of Sandoz, and they had a scientific conference there, but Stan went for the glacier skiing in the summer. And every year the man from Sandoz would come to the lab and we'd have to tell him about our experiments, and none of us were doing anything on Pindolol, to be quite frank. So I thought, well, I'll pay, Stan's done a lot for me, I'll pay one back for him so that he doesn't feel so embarrassed about his free trips to Zermatt. So we did a big study on Pindolol. It turned out to be fascinating. Not so much Pindolol, but how beta blockers work in the human body. And I learned a lot. We set up assays for total body water, extracellular fluid, plasma fluid, interstitial fluid, intracellular fluid, none of which was altered by the beta blocker. But what was altered was the blood pressure. Of course, it was a proper crossover study in about 20 patients. It fell. And with it, the renin fell, the serum aldosterone fell, the plasma noradrenaline, which Peter measured with Barbara Oshikowska, fell, and the serum calcium fell. Well, we may not be so excited about this now, but at those days, how beta blockers worked in the body was a big conundrum. After all, the beta receptor is a vasodilator receptor. You block it, you might think the peripheral vascular resistance will go up. And yet it was the primary form of treatment of hypertension, as you may remember, in the 80s before the advent of ACE inhibitors. And here Stan showed, or we showed with Stan, I should say, with Stan's guidance, that beta blockers inhibit the activity of renin. We now know because they directly inhibit beta receptors on the juxtaglomerular apparatus, and thereby inhibit serum aldosterone, and they lower norepinephrine and the sympathetic drive, and that perhaps is linked in here, since the sympathetic nerves to the kidney are a major stimulus to renin release. So it damps down all of this adrenergic renin system in the body, and that's probably a major reason for how it lowers the blood pressure. And interestingly enough, the biggest correlation that we found is with a fall in serum calcium, which was a surprise and has never really been taken up since, frankly. So then I was particularly interested when I came to St. Mary's in discovering what is the nature of the agent released by the macular denser cells and the juxtaglomerular apparatus that causes vasoconstriction of the nephron during a tubular-glomerular feedback. I'm not going to go through TGF with you, but nevertheless, it's a fascinating problem. And I felt we needed a whole animal model to be able to study release. And chloride activates the tubular-glomerular feedback, so we gave chloride into the renal artery of the dog and measured what came out in the lymph with Stan. And we found that thromboxane, rather than other prostaglandins, came out. And later on, I was able to show in classical micropuncture studies that whereas the TGF in green here is, you haven't got to worry about the units, 11 units, if you block prostaglandin production with indomethacin or thromboxane synthase with this UK drug, or thromboxane receptors with the SQ drug, you block about half of true tubular glomerular feedback. So that early study with Stan, measuring the release of thromboxane into the lymph of the kidney, giving us insight into what's going on in the kidney's interstitial environment, was the stimulus for this finding. So then what was the characteristics, in my opinion, my humble opinion, because I was an observer here, of Stan's terrific contributions? So he never studied anything trivial. He really went for the big prize. And he got a lot of big prizes, starting with the catecholamines, then with the angiotensin, gut hormones, etc. Only used validated models. And I remember, I'm sure David and Peter will remember the unfortunate people who would come to the medical unit and give their talks, and Stan demolishing them. It wasn't because he didn't believe in their ideas, it was the methods always that he got at. He was a terrific stickler for only using validated methods. And I remember actually David coining a new phrase, and after one of these poor individuals had been demolished because of poor methods, David said, yeah, I think we ought to have a new international standard, the STAN, which is a measure of how hard your data really is. And this was only a femto STAN, I remember him saying. And then, as I've tried to illustrate how brilliantly he applied basic science findings to clinical physiology and medicine. He worked at the borderline of science and medicine. Again, he was very strong about this when he went to the Royal College at the end, that medicine was disintegrating into various silos, but actually the excitement is at the junctions, particularly of science and medicine. Very strong on that, and I think very prophetic, and unfortunately ever-increasing weakness in modern medical education and practice. He used new scientific knowledge to improve patient diagnosis and treatment. I tried to show you some of that. and never proposed a human study that you would not participate in yourself, or put your wife in as a subject, I remember him adding, which I think is very good ethical advice. And I'll just finish then with one of the things that I learned from that. So I was very interested in diuretics at the time, and how it is that if we take a diuretic regularly, we get a terrific natriuresis in the first day, less in the next, almost none in the next. What is this breaking phenomenon? And the most obvious answer would be, well, there's volume depletion, and that overrides the effect of the diuretic. So I thought, well, let's actually do that. Let's create volume depletion and see how it affects the diuretic. David's grinning because he remembers this. So I asked David and Peter and some colleagues to help me with this. And so I settled into a bed on Albert Ward, and David bled me 200 mils of blood every 4 minutes until I had lost 1.6 liters, which I knew was just within the range, but beyond that, you get shock. Up to that, it's physiologic response. So this is what we found. I missed a couple of slides, but let's worry. So this was me here, and the blood loss up here. You see the blood pressure completely unchanged. I learned so much human physiology from this one-day experiment. This is a catheter in my right atrium, and you can see that the right atrial pressure beautifully titrates the volume loss. Even the first 200 mils is recognized by the right atrium, and hence the overwhelming importance of the low pressure baroreceptors rather than the high pressure, which only come in with shock. The heart rate goes up, and with it, Peter and Barbara Oshikowska's noradrenaline beautifully showed this rather odd sigmoidal response. I never quite understood why it should be so, and the renin. And at the end of this, two things happened. I got an intravenous shot of 20 milligrams of furosemide, Lasix, and I had just as good a diuresis as I'd had 2 weeks before when I had the same amount of Lasix without volume loss. And so it proved to me that the breaking phenomenon was not due to volume loss, and it was a nice experiment. And then, as I'd written, the blood should be retransfused, and David rather sheepishly said he'd forgotten to add the citrate. So there was a curdled mess on the bottom. So I said, all right, well, we're going to the founts, and I want an equal volume of Guinness in return to restore my blood volume. So anyway, that's a very, very quick and superficial run through some of my memories of dear Stan, for which I owe my career, frankly, because not just of the specific things he taught me, but the way to do science and to apply it to medicine, and to go from basic science to clinical application. Really, it was terrific, and with that went these great discoveries that we've already heard a little about and hear more of, but it was really the method and the approach for me that I shall never forget and has really driven my career. Thank you all very much.
Yes, I'm glad for the reminder that we could replace many of our blood banks with Guinness banks. But Chris, thank you very much. A very great, a lot of memory there. Gordon Stewart's going to talk next about a bit more salt and water. Thank you.
Thanks, David. So, thank you, David and Peter. As Chris was saying, a privilege to be here. I just want to start by adding a little bit about Stan's experiences with Professor Fleming. In his later years, Stan was briefly a patient at UCH, and I took a couple of my students to see him. And he told us that, in fact, under Fleming, he had been the penicillin registrar. And there had been a team of them, with Fleming as the consultant and Peart as the registrar, and no doubt a couple of others, going around the hospital looking for patients with infections and giving them penicillin. And some of them got better and some of them didn't, as we would well understand now. So that would be one thing that he did with Fleming. Now, my job is to talk about salts and water metabolism. And obviously, this, although renin and angiotensin were his primary interests in life and hypertension, salt and water metabolism stands right in the middle between those two. Now, we need to change the slide. How do we do that? Right. Okay. Now, a great many people who are here today, Robert Unwin, David Carmichael, and who we've heard about already, worked with Stan on salt and water metabolism. And a great deal of it was on the mechanisms by which the body responded to having salt and or not salt in the circulation. And what I want to focus on today is just two papers that were published before I was, while I was still a medical student, and before my time on the medical unit. And this is by Linane and, do we have a pointer? No. Sorry? The right arrow. No, not that one. We just want a pointer to go up there. Linane and Carey. It's not showing. Okay, but the first two were working in the medical unit in the early 1970s. And they published in Clinical Science these two papers in 1975. And it's all about, as Chris was saying, the link between the gut and the kidney. And the idea that there might be some kind of messaging link which was activated in the gut and which was relayed to the kidney to produce a natriuretic effect in the kidney. And the first paper was on the rabbit, and the second paper was on the humans. So what was done with the rabbits was to firstly sodium deplete them, and then get them onto the investigating table, and then cannulate them, and then give them either oral salt through a tube, a nasogastric tube, or intravenous salt through that vein that they so handily had in their ears. And a similar kind of study, but not quite so intense, was done on the humans. Okay, so this is a table from the rabbit experiments, and you can see that urinary sodium excretion after the oral salt was given, which is in that line up there, was much higher when it was given orally than it was when it was given intravenously. So 720 to 200 compared with 244 intravenously in the first 4 hours, and this continued for the whole 24 hours. And after 24 hours had elapsed, there was 4 times as much salt was excreted by the kidneys after an oral sodium load as there was after an intravenous load. And, this this is consistent with everyday experience on the wards. When I was in Stornoway after I retired from UCL, we spent a lot of time resuscitating patients with, thank you. We spent a lot of time resuscitating patients. Right, with septic shock, and you give them litre after litre of intravenous saline to try and restore their blood pressures. But you know that in the end, you're going to reach a limit on the amount that you can give because you will sodium overload them and put them into pulmonary edema. And the nurses used to remind me about this. It was well understood on the wards. Whereas you would never hear the same nurse warning the patients on the general ward not to put too much salt on their porridge. You know, oral salt was not regarded as the same kind of dangerous material. Of course, these are not controlled experiments by any means, but you know, this sounds familiar. Now, in the human study, which wasn't as... come on now. Sorry about this. There we are. In the human study, in which they took 15 people, none of which had the initials WSP, all the usual medical students and lab staff, a similar kind of thing happened. So the oral excretion of salt was the excretion of salt after an oral load was always greater than the excretion of salt after the intravenous load. Now, the team must have considered trying to isolate whatever it was that was making this communication. But just as with Stan and angiotensin, one would have had to go to a full-scale biochemistry lab to try and find out exactly what was going on. And it seems that none of them, although they must have considered that, none of them actually did that. And the story was finally solved on the other side of the Atlantic. And it's quite an interesting story. So in 1975, we had these experiments from the medical unit, which set the scene. And then in 1978, Michael Field and others in Boston were looking for the peptide which is made, or the substance which is made by E. coli and cholera and gives you watery diarrhea. And this turned out to be a peptide which activated a guanylate cyclase receptor. Now, the receptor was duly isolated and cloned, and about 10 years later, it was noticed that the receptor itself was widely distributed in the body, not just in the gut, but it was found in many tissues, and in particular, from our point of view, it was found in the kidney. And so it was at this point, it would seem that there might be a physiological system which was widely distributed about the body, which responded to peptides. And so 4 years later, there was isolated from the system a peptide which, as you'll see in a minute, looks like the E. coli peptide, but is of human origin. And then in 1993, crucial to what we're talking about here, another peptide called uroguanylin was isolated from the urine of the opossum. And then in 2003, there was a knockout mouse from the which lost uroguanylin. No. So here are all the peptides. So you see up here in the top row, there are these short peptides, firstly from E. coli, and then from cholera, and this is guanylin and the uroguanylin peptide. Now you can see that there are several amino acids that are conserved throughout these peptides. And it's this one, uroguanylin, which is probably the best candidate to explain the effect that was found in the medical unit in 1975. Its level rises after an oral sodium load, and it acts as a natriuretic peptide in the kidney. Now, we just need to show you the opossum, which I need to tell you is a South American marsupial, which looks like that. Quite why the opossum was used in this way, I don't know, but there. Now, okay, so this is the mouse knockout study, which was conducted by Lawrence and others, also in the States. And we need to concentrate on these two lines here. Now, the open symbols here are the wild-type mouse. The closed symbols here are the uroguanylin knockout mouse. And this is sodium excretion up here after a sodium chloride load. And the circles represent the oral sodium load. And you can see that when the uroguanylin is knocked out here, then the sodium excretion after an oral load is less than the sodium excretion in the wild-type mouse there. And this is the best piece of evidence that uroguanylin is actually the effector of the effect first seen in the medical unit. Now, and this is remembered in the literature, and in this particular review, written in about 2005, you see that the number one reference is the rabbit study by Linnaean. Now, not everybody totally agrees with this, and in an exhaustive review on this subject by Robert over there, it is clearly a complex situation. As we all know, there are many of these peptides. Many of them have actions on the kidney, and many of them have multiple actions, not just a single thing. But it still seems to me that this is the most likely mechanism for the original observation. So I think this was probably a pioneering physiological observation, which probably started on the wards in just the kind of way that Stan would have wanted. And he would have been very proud, very pleased to know that it was yet another peptide that was responsible for this effect. Okay, that's all I have to say.
Gordon, thank you. I'm relieved to know that at last we have an explanation from the Bob Carey, John Linnaean paper. Incidentally, the earliest observation of that phenomenon was lost in a very obscure journal and was done by a group led by a guy called Nowacki, who was working in the German Democratic Republic, but his work disappeared into history. Thank you. I'm just going to say, give two short talks. You'll see on the programme it says transplantation, David Gordon, and then MRC hypertension trials, Tom Mead. Tom is not well enough to be here today, but we do believe he's there at a distance, and I have the pleasure of giving his talk on his behalf. But let me say a word about transplantation first. There we are. And this is an illustration from World Medicine in 1966. This is easy to give because there's hardly anybody around who was involved in transplantation at St Mary's in those very early days. There is only one person who happily is here, and that's Sally Tabor, who was the ward sister on Albert at the time. Where are you, Sally? Yes, there. This article in World Medicine was because a special ward was being opened for renal transplantation, Fleming, and there was Stan talking to Michael Woodruff from Edinburgh, who'd come down to actually open Fleming. Before then, the transplantation patients were nursed on Victoria or Albert, and the little side rooms that were there, which many of us will remember, were actually built for the purpose of barrier nursing patients after transplantation. And I think Sally can actually remember them being built. Yes. But as I say, it was St Mary's was very early in this, and I had not fully appreciated until I started to look into this quite how early. This is a quotation from that same World Medicine article. And as you see, Stan says here that we have been experimenting with transplanted kidneys from cadavers since 1959 and have reached a stage where we can be reasonably optimistic about the results of the operation. 43 patients since 63 and 18 of them still alive. Of course, these days you would get much, much better results, but without pioneering work like this, we would never have got to the position in transplantation that we are now. So there's very little left of the people who are there. There's very little evidence of what goes on because it's now such a routine. Here is not one of the side wards, but James Mowbray outside a plastic tent helping in the treatment of a patient post-transplantation, the plastic tent being designed to isolate them from infection. James, we tried to trace for today, and we're not sure where he is. We're not able to find him. There were a lot of key people. Transplantation is a multidisciplinary thing, and although Stan was very much a driver, thinking that it was going to be a thing that would work for the future, it depended on many other individuals. Here are three of them. There's Ken Owen, who was one of the surgeons involved at the start, on the right. On the left, there's David Sutton. If you look up David Sutton and look for images on Google, you get dozens and dozens of images of Sutton's radiology textbook. He obviously made huge royalties from that, but he was a brilliant vascular radiologist. And interestingly, I had not realised that born into extreme poverty in Manchester and working his way up from there, and a graduate of the Manchester Medical School, of course, and also absolutely essential for the understanding of the process and the understanding of how the kidney worked. There's Ken Porter, who led the renal pathology team right the way through. Another key person in the development of the St Mary's programme is this one, that's Roy Kahn. Roy was at St Mary's for a relatively short time, 1961 to 62, I think something like that. He then went on to the Westminster Medical School as senior lecturer, and then in 65 was appointed Professor of Surgery in Cambridge. And he had worked in the United States using the novel drug azathioprine, and once azathioprine came into the armamentarium of the transplant surgeon and physician, things started to go really well. Roy was the person who said to Stan Peart, I think you should talk to young David, he might be able to do something in your unit. I have undying respect for him. He's not very well in present day, and he's a great age. I have several memories of him. This one is just a little bit more characteristic than the one on the left, but there we are. So that is the history of transplantation, and there's not a great deal that I can talk about in terms of the data and so on, but it was just a pioneering activity. I'm now going to move on to talk about the MRC blood pressure trials. And I'm talking here on behalf of Tom Mead. I'm talking from his script. And when I say I'm speaking with the voice of an actor. I am actually speaking on his behalf. And I believe Tom is listening, and I'm very sorry you can't be here. As we all know, blood pressure was a major interest of Stan's, leading eventually to 2 landmark hypertension trials that we worked on together. I'll say a little about the background to the trials, then go on to their conduct and finally the results and their implications, all briefly. 2 rather small trials from the Veterans Administration showed substantial benefits from lowering mild to moderate blood pressure on stroke, and in particular, and heart failure. There was no effect on coronary heart disease, but the numbers were small. As a result, there was increasing pressure on the MRC for a British trial. This had no easy ride through the MRC because of the cost of recruiting the 18,000 patients who would be needed to give reliable results. And so the benefits for coronary heart disease would be obvious. Eventually a trial was approved and Stan was appointed chair of the Working Party to implement the decision. There were several members of the Working Party who were and still are household names, and I'm quite sure that Stan would have wanted me to pay particular tribute to Bill Mile, who effectively ran the first trial in those aged 35 to 64, and set up and also managed the second trial until he retired. Bill had been brought back to the UK from Jamaica to the MRC Epidemiology and Medical Care Unit at Northwick Park for reasons that were never clear to him or to me. But it was a fortunate move because the coordinating centre was to be at Northwick Park and Bill was appointed scientific secretary. Bill was a devout Quaker and pacifist, so it was surprising that quite by chance his office was allocated the number 007. He served in the Friends Ambulance unit when he was taken prisoner in Crete and repatriated and started as a medical student at St Mary's, qualifying in 1950, but when he became house physician to George Pickering. He went on to carry out extensive work on the epidemiology of blood pressure in collaboration with Archie Cochrane, who he had first met as a fellow prisoner in Crete. Surprising as it now seems, one of the first decisions that had to be made was how to recruit and screen and treat the large numbers of people into that first trial. Various industrial and screen groups were considered, but they weren't suitable for various reasons. Eventually, general practice was considered, tried out, and became the obvious method. Nurses to carry out the screening and oversee treatment were recruited by Greta Barnes. There were 176 practices in the first trial. We recruited people aged 35 to 64 with mild to moderate hypertension, and 17,354 entered the treatment phase. In the second trial, there were 226 practices, older patients aged 65 to 74, and 4,396 entered into the treatment phase. Early meetings of the Working Party were often very stormy, mainly over the treatments to be used, because 2 or 3 members had very strong views on this aspect. Stan took little part in these exchanges, sat listening to them with a slight smile, and then more or less settled decisions when he'd heard enough. Bendrofluozide propranolol were the active treatments in the first trial, with a similar combination in the second. And I endeavoured to find something linking Stan to the MRC and the MRC trials and the MRC trials unit and the general practice framework. This slide has got a caravan and Medical Research Council on the top. Unfortunately, it's probably not relevant because the caption to it says Malawi. So there's something related, but we're not sure. In the first trial, there was a 45% reduction in strokes on those on active treatment, mostly due to the diuretic. You can see those here. However, treatment made no difference to coronary heart disease. All cardiovascular events were reduced by about 20% on active treatment, no difference in mortality from all causes. In the second trial, diuretic and amiloride reduced stroke, coronary events, and all cardiovascular events. That's in the next picture. This became standard management in mild hypertension, but then it's up to others to say how far this has influenced current practice and the advent of many other agents. Results from the trials, especially in the second in older people, have been requested for additional analyses and used by several other groups. And the full details are written up in a book, Mild Hypertension is the Pressure to Treat, by Bill and Julian Greenberg. The main implication for Stan was the demonstration that high-quality data on important topics could be gained from general practice. As he himself wrote, the demonstration that a team of busy general practitioners could successfully carry out a research project of the size of the trials and their complexity was more important than demonstrating whether or not it was of value to treat people with mild hypertension. Stan urged the MRC, the Department of Health and others that what had become known as the General Practice Research Framework should be maintained. This was heeded, led eventually to some 2,000 practices being kept for topics of value and interest to GPs. Not all practices took part in each trial, but GPs volunteered for particular trials according to their own interests. Over the years, the research framework carried out trials in studies of aspirin on primary prevention of coronary heart disease, asthma, psychiatric and other conditions, and in its heyday, the General Practice Research Framework was described by several commentators as the, quotes, jewel in the crown of the MRC. So, as with other areas of medicine, Stan's influence has spread much wider than the narrow confines of individual topics. And Tom goes on and with a little personal note about the later years. I saw Stan fairly regularly in the course of meetings on the hypertension trial. We lived close to each other in Highgate, so we started meeting socially together as well. We had meals together from time to time, Stan, myself, my wife Liz, and Peggy. These were enjoyable occasions until we began to suspect that all was not well with Peggy, and indeed, Stan confirmed that she was showing the early signs of Alzheimer's. Unfortunately, this progressed. Stan looked after her all the time and had her admitted to St Mary's several times when she had respiratory infections and so on. He decided not to part with her at all and took care of her at home as she deteriorated. This was very hard for him, but other than those hospital admissions, he kept her at home all the time. When Peggy died, Liz and I continued to meet him until Stan himself gradually became ill. Fortunately, he was very cheerful during the early stages of his illness, and even as things got more difficult for him. As you know, Stan died at the age of 95. Stan always took a great interest in my work and referred several people to me with puzzling episodes of vascular disease for us to investigate them from the point of view of clotting problems. I've always thought of Stan as a great man on account of his work at St Mary's and as a trustee of the Wellcome Trust. I had to consult him fairly often about aspects of the hypertension trials, and although he travelled frequently, especially for the Wellcome, he always seemed available when I needed him. So that's Tom Mead speaking and writing, and thank you very much, Tom, for that. Of course, it's a slightly downbeat thing to think about Peggy and then eventually Stan dying, and I think it would not be characteristic of Stan to want me to end any talk on a downbeat note. So here's a cheerful picture of the party in the 1960s when Stan actually retired from St Mary's, 87. Thank you, Jerry. Here we were in Italy. A lot of those present here today are visible in the picture. I think there's Robert Unwin there. There's some other chap with a beard somewhere around here. That was me. There's Poulter. There's Stan and Peggy. And I think many of the others were here. And indeed, many of the others that Peter has mentioned who have since deceased. We should say it's very nice that we've got Jerry McCarthy here, because I think she organised this entire party, didn't you? Yes. So thank you. We are going to break for coffee in a minute, but we've got a minute or two for any questions, either for me, or for Chris, or for Gordon.
Can I just make one comment?
Yes, please.
Right at the end.
Could you use the microphone? No, just come in.
Oh, right. The first renal graft transplantation took place in the Lindo wing in 1961 on the second floor, and there were 5 nurses selected to go and nurse Mr. Griffin, who had the first transplantation. And there was James Mowbray involved and Professor Peart, and I think Ken Owen did the first operation. And Mr. Griffin, he lasted 10 days. The second child was a little boy called Christopher Leggett, and I was very lucky to be able to nurse him too. So it's a little earlier than you're saying.
Well, yes, I mean, well, I thank you. That's fascinating. In that quotation of Stan's, he said they'd started cadaveric transplantation in 1959, which doesn't fit with the 61.
Well, it may be I was just trying to work it out on my hand when I actually started my training and when we were asked to do so. It might have been earlier.
Yes, 66 was when Fleming was opened as a ward specifically for transplantation. But Sally, I don't know if you have a memory of when you first started seeing transplant patients on Albert.
I didn't actually start until 67, so at that stage they were certainly between Albert, Victoria and Fleming, so certainly not in the Lindo wing, but yeah.
I think there's a question. Peter's got a comment.
My only contribution to that was I was Ken Owen's houseman in 1968 and used to assist both Ken Owen and the vascular surgeon at the same time.
Felix?
Yes,
Yes.
doing transplantation.
Yes.
And that was 1968.
Yes. And my acquaintance with transplantation, of course, started in Cambridge with Roy Kahn, particularly waiting for that magical moment when the vascular anastomosis has been made and the transplanted kidney starts to drip urine into the operating field. It's absolutely magical. If there aren't any other questions, I think we're keeping everyone from their coffee. It is the coffee break. We are meant to start again at 12, and I think to get back towards time, we must endeavour to do so. But thank you for everyone for the contributions so far. Thank you. Just before we start, I should recommend to you the moving slideshow, which has just now gone off, but it will reappear. There we are. Katie Livingston, who's not here, and I spent a very happy morning going through the mountain of pictures that Stan's family provided, and a few others we could find. And there are some very serious ones, but there are also some very nice ones as well. And that's Joe, who's out in Zambia at the moment. But anyway, our next speaker is Katie Core, and who's going to talk about trials and epidemiology. Katie.
Good afternoon, and thank you for the invitation to come and speak at this celebration. I was enormously fortunate to be a house officer on the medical unit in 1976 with Sir Stanley, and then I came back in 1979 as a Wellcome Trust Clinical Research Training Fellow in Medicine and Epidemiology with Geoffrey Rose. And I have to say that those were, I couldn't be more fortunate in the people who I learned from. You will have heard a bit about the tradition of Sir George Pickering, and in the 1950s there was the big debate about the nature of hypertension. Lord Platt insisted that hypertension was inherited as a dominant characteristic and a specific disease in the population. You might say that George Pickering was one of the early epidemiologists. If epidemiology is defined as the quantitative study of the causes and control of diseases in populations, he epitomizes approach when he said this was hypertension was a continuous variable. It's the basis of the epidemiologic approach to the study of blood pressure in populations. And actually, this was adopted by Sir Stanley when he gave his Croonian lecture on concepts in hypertension in 1979, when he actually supported these definitions of hypertension, quantitative assessment. Never define, describe how much. Could be a statistical deviation from either the mean of the whole population or from the young adult. The level associated with increased future mortality and morbidity, and this is the reason that we are interested in hypertension, for by and large it's largely an asymptomatic condition. And this was elaborated on further by Rose. In terms of clinical implications, it's the level at which benefits of treatment or action outweigh non-treatment. And the reason this is relevant is that if we look at the population distribution of blood pressure here, you can see it's a normal distribution, and the red line indicates the rise of the risk of morbid events associated with the increasing level of blood pressure. It is quite clear that at the very highest levels of blood pressure, the risk is very, very high of subsequent adverse cardiovascular events or mortality, but that this risk is continuously ranged in the population. The higher your blood pressure, the higher your risk. So the optimum blood pressure to have is actually the lowest. And as you can see in the distribution, those who have what we might consider normal blood pressure, 120 to 140, many of us in the population still at increased risk of adverse events compared to those at the lowest levels. And it was because of this discussion about when should we treat high blood pressure that some of the trials were initiated. And we've heard earlier from David Gordon and Tom Mead about the hypertension treatment trials. So the question is, we know treatment at the very high end is beneficial. What about in the middle range, moderately elevated levels? And so these two landmark trials, of which Sir Stanley was chairman of the Working Party, established very, very clearly the benefits of treatment of hypertension, whether in mild hypertension or in older adults. At that time, there was quite a nihilistic approach to blood pressure treatment in older people because it was said it's normal for blood pressure to go up with age, and therefore we shouldn't treat older people. The MRC treatment of mild hypertension was actually much more important in what it showed us about the dilemma of treating hypertension. It's quite clearly showed, as you've heard earlier, there's a 45% reduction in stroke. So big benefit. But because the absolute level of strokes is not high, the absolute benefit was limited. 850 individuals need to be treated for 1 year to prevent one stroke. And that has led to a lot of debate about is it or is it not worth treating it in hypertension. The absolute benefits in treatment of older people are much greater because their event rates are higher. But this also led to the question and the dilemma in terms of how much impact does treatment of hypertension have on prevention of cardiovascular disease in the population. This is a similar slide to the one that you saw earlier. The light blue distribution is the normal distribution of the population. The red line is the increased risk associated with level of blood pressure. But the dark blue bars indicate the proportion of adverse events that happen in the population related to different levels of blood pressure. And the point I want to make here is that while people with extremely high levels of blood pressure contribute a certain proportion of events in the population, the vast proportion of strokes, heart attacks that happen in the general population occur in those of us who have moderate or mildly elevated levels of blood pressure, just because there's so many of us. So economists have recognized this for ages, that the greatest profit you make comes from the large numbers of people from whom you make a very small profit, rather than the tiny number of people making a great profit. But this leads to the dilemma for prevention. If we want to prevent the large majority of strokes and heart attacks that happen in the population related to high blood pressure, do we start then treating the entire population, lowering the threshold? But we know for the individual, the benefits are not great. And this is what led to Jeffrey Rose's two complementary approaches to prevention. One is the standard clinical approach, in which we treat those with very high levels. We screen and identify very, very high levels of blood pressure, treat them, push them below the threshold. And the second, which is to try and shift the whole population distribution of blood pressure in optimum direction. And he estimated that if we even shift the population distribution by 1 to 2 millimeters of mercury, very, very small individually for an individual, we might achieve as much population benefit in prevention of cardiovascular disease as by treating all the hypertensives above a certain threshold. But this then leads to the question, what determines population levels of blood pressure? Why does this population have so much disease? And Sir Stanley had a lot to say about this too. When discussing concepts of hypertension, he postulated that this was environmental stimuli on a very strong genetic background, and he listed possible environmental stimuli, all of which have led to our further studies, epidemiologic studies: social stresses, alcohol, hormonal status, salt, ethnicity, environment. So when I was the research fellow, I had the opportunity to go to St. Lucia to conduct a blood pressure survey, house-to-house survey, collecting urines, measuring blood pressures, which we measured in the medical unit when I came back. And the interesting thing about the blood pressure patterns in St. Lucia was this was a black community known to have high blood pressure, known to have very, very high levels of sodium because they ate a lot of preserved meat, salted fish, salted meat. But interestingly, their average blood pressures, you can see on the graph, they're the bottom lines on this, the graph up there. They had lower mean blood pressures than two other black populations, the Caribbean, Jamaica and St. Kitts. And the interesting thing about the St. Lucian population was largely agricultural. They ate a lot of plant-based food. So as well as having high salt in their diet, they had very high dietary potassium derived from these vegetables. And in the urine samples that we analyzed subsequently, we observed an inverse relationship between blood pressure and urinary potassium, suggesting the hypothesis that high dietary potassium might protect against the blood pressure-raising effects of a very high sodium diet. So we were able to test this when we came back to the medical unit in doing a randomized double-blind crossover trial in normotensive individuals. And these individuals had average blood pressure of 118 systolic, 73 diastolic, so not hypertensive at all. But in this study, giving potassium versus placebo resulted in a significant reduction in blood pressure. I was then able to do some time in the University of California, San Diego, with Elizabeth Barrett-Connor, where she had an ongoing prospective population study. And the interesting thing about this study was she had collected a lot of blood samples, a lot of urine samples, a lot of data at baseline, and then followed up the cohort and were able to document subsequent cardiovascular disease mortality in this population. And we analyzed the dietary potassium at baseline and looked at subsequent stroke-related mortality. And the graph that you can see there showed an inverse relationship between baseline dietary potassium intake and subsequent stroke-related mortality, a dose-response-related relationship in both men and women, and those in the highest third of potassium intake had no stroke-related mortality. The estimated impact or size of relationship was about 10 millimoles a day increase in dietary potassium, equivalent to about 1 serving of fruit and vegetables, was associated with a 40% reduction in stroke risk. We were also able to follow up hormonal hypotheses relating to cardiovascular disease and looked at stored blood samples of dehydroepiandrosterone sulfate, DHEAS. It's the most abundantly produced steroid hormone in the body, goes up with aging, and found also, independent of other risk factors, it was inversely related to mortality subsequently in the next 9 years. So we were able to observe a relationship between potassium intake and endpoints as well as blood pressure. It shows you how difficult it is to study these things in randomized trials. It's only this year, a few months ago, that a colleague, Bruce Neal, published a trial, 5-year trial, in which he showed that salt substitution, i.e. 25% substitution of potassium chloride instead of 100% sodium chloride, was associated with reduced stroke, cardiovascular events, and deaths in high-risk individuals in China, about 13% reduction. So supplementation or substituting potassium chloride for sodium was associated over 5 years with reduction of cardiovascular events. Back in Cambridge, we had the opportunity to start a new prospective study, and I'm delighted to see Sir Keith Peters here, because he was the one who appointed me from a part-time retraining senior registrar to the post of professor in clinical gerontology. I don't think anyone else in the world would have taken such a terrible risk. But anyway, we were able to establish a prospective cohort study, learning from the lessons we had in Rancho Bernardo, where we recruited 25,000 men and women aged 40 to 79 years from GP stage 6 registers with extensive lifestyle and biological information, including lots of blood samples, lots of questionnaires. This was part of a 10-country European prospective investigation in cancer and nutrition to try and identify why different populations across Europe have such different levels of cancer, heart disease, diabetes, etc. And the key person in that was Elio Ribili, who is now emeritus at Imperial, but was at that time in the Imperial College is now in Imperial College, but was in the International Agency for Research into Cancer. And this was to expand on our trying to identify lifestyle determinants of cardiovascular disease as well as blood pressure. And just show you one result from the study, we identified 4 positive health behaviors. 1, you score 1 if you are a non-smoker. You score 1 if you are a moderate alcohol drinker. You score 1 if you're not a total couch potato, anything beyond doing nothing the whole day. So an occupational, standing occupation was better than being non-inactive. And 1 if you had a blood vitamin C more than 50 micromoles per liter. Blood vitamin C is a very good biomarker of fruit and vegetable intake because we do not manufacture it in our bodies. That indicates about 5 servings of fruit and vegetables a day. And if we can score 0 to 4 on these health behaviors, on the left, we can see the survival curves over the next 14 years, according to whether they had 0, 1, 2, 3, or 4 health behaviors. On the right side is the relative risk of mortality from all causes, cardiovascular disease and cancer, showing that between 0 health behaviors and 4 health behaviors, there's about a 4-fold difference in risk, graded across the whole distribution of number of health behaviors. This difference was equivalent to about 14 years in chronological age or life expectancy. And it wasn't difficult to have these 4 health behaviors in a free living population. 25% of this population were practicing that. So if we want to expand that further, because Sir Stanley was very interested in genetics, we've heard a lot more about polygenic risk scores now in the general population. And we also did whole genome studies in the entire population. And what I can show you from the slide is that polygenic cardiovascular risk, coronary heart disease risk in this case, is normally distributed like any other risk factor, blood pressure, cholesterol, etc. So the vast majority of cases don't happen in those at very high genetic risk at the top end of the distribution. They happen in the middle of the distribution. But what I've also done is show you the mortality, subsequent mortality for coronary heart disease, incident coronary heart disease, according to number of health behaviors. And as our genetic risk score increases, so our risk of coronary heart disease increases. You can see that. But if you stratify by number of health behaviors, the ones with the 4 health behaviors, the green line at the bottom, yes, if you have a higher genetic risk, you have increased risk of coronary heart disease, but the absolute risk of coronary heart disease was lower at the top end than those at the bottom end of the genetic risk score, that blue line, who had less than 2 health behaviors. So health behaviors completely out-trumped in the genetic risk in terms of subsequent coronary heart disease risk. So I think it just illustrates how strong the support is that Stan gave to epidemiology and the 2 statements he made in his Science and Medicine Implications for the Future. First of all, one of his heroes was Stephen Hales, and his most important contribution was to introduce mathematics into biological subjects, quantifying risk. And he also acknowledged the important role of the causes of causes, the role of public health, fundamental reasons why people have different health behaviors in whole populations, and the potential impact that it has. But the most important thing that I think I learned from Stan was what he said in this paper. He was always challenging. He was always disbelieving of accepted wisdom, always questioning. And I think he's said it very clearly. There's no absolute truth, only a set of probabilities that we have to constantly test. And I remember how he constantly challenged himself when looking at patients. And the prescience of this, major biological changes in the populations have a price. So whatever we found in the past as scientists may not apply in the future. And this was why he said it is so important. It's not the findings, it's the people. You have to have the continuing process of people who carry on adding to the evidence, noting new discoveries, and finding out, facing new problems. And I think what we are eternally grateful for is what he actually did in practice, supporting all of us in scientific and medical pursuits, and the difference that he made to all of us in teaching us what it is to be a true scientist and clinician. So thank you very much to Sir Stanley.
Katie, thank you very much. I just take Chairman's privilege to make 2 comments. One is that you showed Jeff Rose there, and Peter earlier on said that Stan was an absolutely brilliant clinician. I would say Jeff Rose was almost as good, a very, very fine clinician indeed. The other comment is that there is one other professor somewhere who just might take the risk of appointing a young person completely out of the blue. Not just Keith would do it, Stan would do it as well. Next, Neil is going to talk about migration. Neil Poulter.
Good afternoon, everybody. Thanks so much indeed, David. I'd like to start by thanking David and Peter for inviting me, including me on the programme. Absolutely delighted to be here. So it's my job to talk about the migration story, and as you may appreciate, I was the sort of project manager who was shipped out there to try and make the migration story work. The brains behind it were 4-fold. First of all, Peter Sever and Katie in the audience, and then sadly 2 can't be in the audience, Jeff Rose and Stan Peart. So those 4, I give this talk on their behalf. So the idea of the migration story, the migration study, the Kenyan Luo migration study, was to try and get to the etiology of high blood pressure. And as Katie pointed out, in the background, in the run-up to this, about the etiology, had been this debate between Lord Platt, who was dealing with the genetics, he believed, whereas George Pickering had a totally different view. And there's a great quote from George Pickering, which I think is worth showing. Essential hypertension is a type of disease not hitherto recognized in medicine, in which the defect is quantitative and not qualitative.
It's difficult for doctors to understand and medical students because it's their departure from the ordinary process of binary thought to which we're brought up. Medicine in its present state can count up to 2, but not beyond. Meanwhile, an anonymous quote about this debate said that while Pickering is bickering and Platt's pratting, hypertension remains a burning. It was an increasing big problem. And another good quote from the time was from Geoffrey Rose, who said he was a medical registrar at the time, and he well remembered the widespread bafflement which greeted this famous professor of medicine when he asserted that hypertension, in which he was a world expert, didn't exist as a distinguishable entity, causing great confusion. However, what we did know, and these are data from, typical data from westernized countries down here, this looks at the prevalence of hypertension with age, and it's what everybody expects, higher in men than in women until older ages, but essentially a steep rise in the prevalence of hypertension with age. And this was alluded to a little bit earlier, that we expect blood pressure to rise with age. It is not normal for blood pressure to rise with age. It is usual for blood pressure to rise with age. That's what should happen. Once you get to full adult maturity, blood pressure should flatten off. That is normal. That is usual. It's normal to die of cardiovascular disease in the UK, and that's why it's usual, or rather normal, for blood pressure to rise with age. But actually, this is the normal situation. And there have been several of these, 20-odd of these populations in the world where blood pressure doesn't rise with age. Here are 4 that were written up in the Intersalt study, and we contributed the Kenyan population. But basically, blood pressure doesn't rise with age in these populations. And there have been other studies like that showing that blood pressure doesn't rise with age. What they had in common was that they were all non-industrialized, they were rural, they were remote. They tended to have low blood body weight, they had low alcohol intakes and low salt intakes. And so the idea was that whatever it was the process of development. It took people from these types of populations, remote, rural, and they then developed. And that process of development was associated with a whole series of risk factors that you'd recognize. People get older, they exercise less, they drink more booze, they eat more salt, they got less fresh fruit and vegetables, body weight goes up. Stress, well, I don't know which way, I think probably the stress just changes. Smoking goes up and saturated fats. Now, you don't have to be an erudite audience like this one to appreciate if you do that in a population, then you're going to get a huge increase in cardiovascular disease. And most of these will be driven by raised blood pressure. These are risk factors for raised blood pressure by and large. So, the idea was for the Kenyan Luo migration study, to work on a migration study, was to try and determine what it was in that process of development that caused hypertension. So if you look on the left-hand side, the usual situation of increasing age, systolic blood pressure going up, and on the right-hand side, the usual situation in a westernized population, that normal distribution, we take an arbitrary cut point, inappropriately, but we do an arbitrary cut point and say, okay, everyone in there is hypertensive. So what we wanted to do was try and find a population where the blood pressures were low, and these were in unacculturated populations. That doesn't mean a lack of culture, it means they haven't taken in cultures from the outside. And we look at try and find one of these low blood pressure populations, which has a distribution shown here, which doesn't include hypertension. And what we wanted to do was to watch that transition from an unculturated population to that. There had been cross-sectional studies. Peter did one in the Hosa. You saw that later. Jerry Shaper did it with the Samburu. And the Easter Islanders were looked at in the Easter Islands, I think, when they went to Chile. So you've got a sort of rural-urban comparisons, but no one had followed them through, the same individuals, from one situation to the other. So the idea was to find this population, see them moving into that situation and watching their blood pressures rise, which meant their shift in the blood pressures went to the right, and therefore we got to the etiology of hypertension. So that was the theory behind the plan. So stage one was to find a low blood pressure population. And at the second attempt, we did that. We found a low blood pressure population on the north shores of Lake Victoria, the Luo tribe in Siaya district. And the initial 861 people we looked at, and these are their data, were randomly selected from this population of about 20,000 people. And these, I show here the data for males, and these are their systolic blood pressures, and you can see pretty flat across the age range. Now this is a picture of where they came from. It's absolutely beautiful. No electricity, no running water. This was remote Africa. Nobody was overweight. It was absolutely beautiful. It just came up from Lake Victoria. Next thing to do is we wanted to find out and make sure that the population we were going to look at and hopefully track from that rural area moved in sufficient numbers into Nairobi for us to be able to follow them up, capture and get hold of them and then follow them up over time. Was there enough migration taking place? And this was initially we thought we were going to try and look at the Maasai. And I remember meeting the senior chief of the Maasai in a bar in Nairobi to discuss the possibility of doing the study. And he said, oh yeah, he knew the Maasai did move into Nairobi. I said, fantastic. He said, can you track them? He said, yeah, I can name them. And he was able to, which made an epidemiological study a bit tricky because the numbers of Maasai that went into Nairobi and then stayed there was tiny. They would come in, but then go out. So we need a population that migrated into Nairobi and sufficient numbers stayed there. So we then, at the second attempt, we found this group, the Luo, these are the rural data I just showed you. Here are the data of some urban rural, and we did this by contact tracing. We went to the rural area, said, has any of your relatives gone to live in Nairobi? Yes, and we went and tracked them. We found everyone that we found, and we found just about all of them. Absolutely all of them agreed to have their blood pressures, and there you see the difference. So we were in business, pretty flat, and a serious rise with age in the blood pressures. And there were enough numbers we could find the people. This, by contrast, was a typical Nairobi slum. This is Mathare Valley. And that guy there was Dominic Onono, who was one of our trackers who would help us to find people within the slums and track the people down. No numbers on the doors. This was not easy. And a whole mix of tribal groups. But Dominic would find people, and he did that initial cross-sectional survey, showed the blood pressures rise. So the next bit of the game was to set up controls of new migrants and rural controls. We needed to get up this cohort, I'm sorry, that should say, setting a cohort of new migrants and rural controls at baseline. And it turns out Dominic was able to find people within a month of them leaving the rural area. In the rural area, we had people going around these homes of about 30,000 people, 35 villages, going around checking, has anyone gone to the area into Nairobi recently? And we found them, Dominic found them within about a month of leaving. And then at 3, 6, 12, 18 and 24 months. And we measured their blood pressures, lying blood pressures with Hawksley random SPIGs. And we collected 3 overnight urines. We've done a whole lot of work on spots, 12-hour, 24-hour urines to validate what we were doing, but we had 3 overnight urines at all these stages and compared the two. It seems heartbreaking to be able to show the results really in one slide after 5 years of doing this, but that's pretty much what I'm going to do. And that's it. It was actually different for systolic, and I'll come back to that. These are the diastolic pressures of the men, and here you see them at 0 months. The migrants, and we had 325 migrants in the frightening yellow, and there you see a little bit to the right, but fairly similar. But then the controls here versus the migrants, and there were 267 controls. The controls came from the same village, their age and sex matched. So they were as close as we could do. Over the 4-year period of the migration, we took the middle 2 years and matched the controls there and did them as a cohort together. And you can see here, as Katie alluded to, this idea of shifting the population. It just moved to the right. And there you see it. Now, the systolics and diastolics were different. At baseline, at 0, actually 1 month, the systolics were already 10 millimeters higher amongst the migrants. In fact, both groups, the migrants and the controls, their blood pressures fell systolic over the 2-year period, but the gap widened. The migrants had higher, but they widened, acclimatization presumably. Whereas the diastolics in the two groups, amongst the controls, the diastolics fell over the 2 years, whereas in the migrants, the diastolic rose. And as you see this important shift of the whole population. There were no genetic subgroups that got hypertension. When we look at what the major determinants of that were, the best correlate really was the sodium-potassium ratio, which came back to Katie's point of what she saw in St. Lucia. It was the sodium-potassium ratio of the urines that was one of the strongest predictors. Pulse rate was up about 2 beats per minute amongst the migrants, and that remained throughout the whole 2 years. And body weight went up really quite quickly. Just as I said, the systolic had gone up by about 10 millimeters in the first month. The body weight went up quite quickly. And that didn't seem to fit with the energy intake. We did dietary histories and stuff, and the analysis best we could do suggests they didn't have higher calorific intake. And actually, they exercised more in the town, because they were mainly men looking for jobs, than they did in the rural area. And on the basis of that rapid rise in systolic, which seemed greater than you would expect from the increase in the sodium. The sodium went from about 60 millimoles in a day to about 100, 110 when they were in the city. That didn't seem to fit with a 10 millimeter increase, and it was really that got Peter to devise this theory, this hypothesis, which he published, and he showed you this earlier, so not to go over it too much, but basically just the fact that the increase in dietary sodium, the increase in systolic seemed disproportionately large. So it was really the idea of the dietary sodium here. Normally you'd get sympathetic outflow would be reduced, but in the presence of stress, in our case, sympathetic tone is referenced by 2 blood pressures, 2 beats per minute, rather, of the pulse rate, that would at least maintain the sympathetic outflow, possibly increased it, and that slowed the usual response of the kidneys getting rid of the salt, stopped that happening, fluid retention, so the weight would go up, and the blood pressure went up. So this fitted very well what we'd observed. The sodium and the potassium we knew had changed. The pulse rate went up, that's the stress, and then that gave us the weight and the blood pressure increase that we saw so quickly. So that really was the story in a nutshell and what came out of it. Since then, if we fast forward to the last year or two, there's been something of a controversy about salt intake, and the idea that salt was bad for blood pressure at the population level has been questioned largely by Salim Yusuf and some of the data he's produced almost exclusively on spot urine samples from the Pure study and other studies. He suggested that there's a J-shaped curve, and at low salt intakes you may be getting an increase in cardiovascular events. And the only thing I think what the migration story, our migration story, contributes to that is that in the 5 years that I lived there, in this population of 35,000 people, I never saw a stroke or a heart attack, nor any diabetes. And I think I would have done. I did a clinic there pretty regularly, and people used to bring sick people, or I was taken to people. There never was one. If there was a J-shaped curve in 5 years, I think I would have seen it associated with low salt intakes. It was absolutely, these were very low salt intakes throughout the rural area. And difficult to argue with Salim Yusuf, for those of you who know him, but I think he's wrong. Again. So with that, thank you for your attention.
Neil, thank you. Not to keep everyone from their lunch, but we do have time for a few questions for Neil or Katie, if there are any questions. Chris, could you hang on for the microphone?
Lovely, thank you. Two wonderful talks. Thanks very much. Katie, can I ask a specific question? One of the more embarrassing things you can ask an endocrinologist is what is the function of the steroid that we all produce more of than anything else, namely DHEA sulfate. You had your prospective study published in the New England Journal of Medicine there. We now effectively know what DHEA sulfate actually does, and that the control of HS-carb, which of course is a key ROS sensor, and that is absolutely vital. That's really what's happening. I'm just interested as to whether or not you feel we've now got any decent prospective data of people being given replacement therapy with DHEAS.
I don't think there's been any. There's a suggestion of doing randomized trials, but I don't think the proper randomized trials have been done. But the findings have been replicated in other studies. The slight caveat on that is that when we looked at it in women, this was a study in men, we didn't find the same relationship. So we have to be a bit careful about generalizing. But what is slightly alarming is based on observational data that lots and lots of people are taking DHA supplements. I mean, you can look on the internet.
Any more questions? Oh, right at the back. Sorry. Eldred.
Eldred Parry. I'd like to comment, if I may, rather than ask a question, and say that in Ghana, one of my former students, and John Eastwood from St. George's, carried out studies in villages and denied people salt over a period, and then we introduced and found indeed that this was associated with a lower blood pressure. In parallel, and this is not in the realm of scientific study at the moment because of the logistics, we have found in following up populations in southern Ethiopia that there is high blood pressure randomly in the rural clinics served by health officers, not people with hospital seeking wishes. And it appears throughout the continent that there is a readiness to maybe enter that cycle. In parallel, in the similar populations, John Britton from Nottingham found that kerosene stove introduction into a large urban community was associated with an increase of asthmatic symptoms. So there were structural changes in society in rural areas. And the other question, which I think your study doesn't really answer, is what sort of people moved from the rural area to the urban area? That's all I have to say. Thank you.
Eldred, thank you. Any further comment or questions? If not, we are due to break for lunch. We have a little bit over an hour for the purpose. When planning this meeting, we allowed for quite long coffee breaks and quite a long lunch break, given that there will be many people here who have not seen each other for 10 years, 20 years, sometimes 40 years, and we will all have plenty to say to each other. So thank you to everyone who's contributed this morning, and we return at 1:45 when Peter Sever will be in the chair. Thank you all very much, and enjoy the slideshow.
1, 2. Check 1, 2, 1, 2. Check 1, 2, 1, 2. Mic check 1, 2. Check 1, 2. Good. Yeah, I think it was more of the green ingredient.
Could I ask you to take your seats, please, so that we can get underway precisely on time. It's my pleasure to chair this afternoon's session, and we're moving away from the renin system and trials in epidemiology, and it's my great pleasure to introduce Chris Mathias. And he was the second member of the unit who, like me, had departed from the field of renin. I'm really looking forward to his talk on the autonomic nervous system. Chris.
Peter, David, and in particular, the Peart family. It's a pleasure to see you all, Celia, Sarah, and Robert. And some, I believe, are watching online. Would that be right? Which is great. Thank you very much, by the way, for the invitation to talk about an area which some decades ago there was little known about, other than on the scientific side, as Tilly has told us, an enormous amount. The autonomic nervous system produced an enormous number of Nobel Prize winners. They lagged behind in terms of the clinical side. And I'm going to focus on what Professor Sir Stanley Peart did, particularly since 1973. I'm just going to go on to the next slide. I first met Stan, and I've had permission to call him that, just in the week before Christmas, 1973. This was his office on the 3rd floor. It was surrounded by hordes, I think might be the word, of Christmas cards and various gifts. And he was so hospitable, but was very, very clear as to what I was there for. And we went over this. And the reason for that is on this slide. This was before meeting him. I qualified in 1971. This was in Bangalore. At St. John's. At 72, I was fortunate to get a Rhodes Scholarship from India to Oxford. And there were a few difficulties when I first came in terms of what I wanted to do and what I could do. And more importantly, I was clear as to what I did not want to do, as it were. But I was fortunate that the tutor at Worcester College, where I was, pointed me in the right direction and said, why don't you combine neurology with cardiovascular issues? And the right person was Dr. John Spaulding. John was a neurologist who made his name and fame during the polio epidemic in 1955, where he worked on respirators. And he noted that a number of the patients had problems with their blood pressure and their heart rate, particularly those who we later studied who had Guillain-Barré syndrome and other autonomic issues. And so he really made the autonomic side, the cardiovascular side, one of his strengths, as it were, over the years. And so when I went to speak to him, he said, well, there is a project, he said, looking at patients who had tetanus on ventilators. They had both hypertension and hypotension. You couldn't do much work in Oxford because they had usually one every year who was on a respirator because of the efficacy of the vaccination program. And so in early 1973, I joined a team from his group which went to Nigeria. In the winter season there, the dry season, the incidence of tetanus rises markedly. Now, this was an amazing experience, particularly practically, because those days the only way to measure blood pressure continuously was to put a catheter into one of the arteries, peripheral arteries. It's something we don't do these days, fortunately, unless particular reasons for that. So it was amazing, except there were no results, which made me have to think about what was going on. And this is where the model came in, when I was looking at the work which had been done by them in people with high spinal cord lesions in particular. Now, in the middle is a schema drawn by our daughter some years later to make it simple for me too. And it shows the afferents going into the this is the tetraplegic going into the spinal cord, the vagal efferents. And if you've got a complete lesion, there's no cerebral control over the sympathetic outflow. The sympathetic outflow is not destroyed, and this is different, therefore, from patients who've got autonomic failure, where you could have lesions right down the neural axis. These patients, therefore, appear to be the group to study if they were complete, and therefore you knew it was almost like having an experimental animal model, as it were. the work on the cardiovascular aspects had been done, but von Euler and Axelrod had won the Nobel Prize a few years ago for their work on noradrenaline. And it did strike me, why don't we look at various substances which raise blood pressure or which lower blood pressure? And the three which came to mind were noradrenaline, angiotensin II, and the prostaglandins. Now, the problem was actually finding somebody who would measure these substances. And the first led us at the time, we didn't know Peter at that time, led us to Scandinavia with Niels Christensen. And this had been organized, in fact, by my predecessor. On the renin-angiotensin side, it was, of course, Stan Peart, and that's what took me to Stan to see, would he be interested in these studies? Would he be in agreement with measuring noradrenaline, angiotensin, at that time, plasma renin activity, and aldosterone? And I'll just show you, in a way, what happens to these patients, because to give you an idea, when a tetraplegic is upright, as you can see here, normally there's no change in blood pressure and heart rate, but in a tetraplegic, the blood pressure falls markedly, orthostatic hypotension. The heart rate rises dramatically. That's because the vagus is intact and tries to compensate unsuccessfully. And therefore, the measurements of renin and aldosterone, along with noradrenaline and prostaglandins, were made. I think Stan must have been slightly concerned, I suppose, because he did offer to have, because I was pretty green, as you can imagine, at that time, one was supposed to be doing intra-arterial cannulations. So he offered to have Tim Goodwin, who was a senior registrar at the time, to come down to Stoke Mandeville to do the studies. And this was a great help because I didn't have much if any, hands on the ground, as it were. And this slide indicates, don't look at the axes, there's something amiss there. If you look at the continuous line, that's the renin level going up with head up tilt, and then falls, and that's the aldosterone level going up later. And this was not what I predicted, because I thought with no sympathetic activity, because noradrenaline did not rise when this happened, this shouldn't have happened. But Stan, in fact, he said, well, you started with a hypothesis, these are your results, now work on them, he said, which I did. And this was really most educative, as it were. He was also very interested in going on to the next stage. This is studying people, again with high lesions, complete lesions, who had what's known as autonomic dysreflexia. So when the bladder, for instance, that's below the level of the lesion was stimulated, the blood pressure would shoot up, the heart rate would fall, because that component of the baroreflex was intact, and the noradrenaline levels rose. Incidentally, these gaps here are where blood was taken, because these were all intra-arterial records going back, almost 45 years or so or more. The renin levels, by the way, did not rise. And this led to a whole series of studies indicating that certainly in man, renin could rise independently of the sympathetic nervous system, unlike had been thought previously. This was part of my DPhil thesis. I was fortunate in completing this. Roger Bannister was my external examiner. And then I had a dilemma. What was I going to do? I really was so fond of the field, the autonomic field, and I wished to continue. But my various mentors did say, well, this was not something to aspire to. It did not exist. It was a pipe dream. So I was sent along into the sticks, as it was called. Not I was at the Hammersmith at the time, but they said, go elsewhere, into the country almost, get experience, and then think about it again. So I got my membership, and Stan was, of course, so helpful. I would ring him or times write, and he would come back with advice, which was absolutely invaluable. He tried to point me towards neurology or cardiology, the main streams, as it were, but he realized soon that that's not what I wanted. It was this. And then he completely surprised me by saying, why don't I join him? Which floored me. And this is what happened. You couldn't just join him, you had to have a proposal. This went up to the Wellcome Trust. I was very fortunate to work, and I got a grant for 5 years to work with him in the medical unit. Now, I hadn't realized, in fact, I thought it was 5 years only, and Stan used to be in that area, and the medical unit, the laboratories were in the other side, the medical school side. I hadn't realized that this would be 5 years. I'm still there, by the way, on the academic side, and we're not necessarily physically. So it's been a lifetime, as it were, and I have absolutely no regrets at all about that. We worked initially, and I'm not going to give you details, and there are various people here, David Carmichael, I'm just thinking of examples here, looking at central and peripheral autonomic mechanisms in renovascular hypertension in particular, and of course in spinal injuries that continued at Stoke Mandeville. At the time, Roger Bannister was both at St Mary's and Queen Square, and Stan was very encouraging in terms of linking up with Roger, which I did, and this gradually grew, hence the studies with autonomic failure patients, and this accounted for why 5 years later I was fortunately again awarded a senior lectureship, but this was both between St Mary's and Queen Square. Now, there are a lot of exciting studies which were done at the time, and I have no time to talk about it. One linked up with Chris Wilcox, the use, and Stan did like this. You had to find out the pathophysiology, and if you could, the treatment. So desmopressin, food-lowering blood pressure, peptides, octreotide, exercise-induced hypertension. We haven't quite got there as yet, with effective treatment, targeted treatment, and rare disorders also, such as DBS deficiency, where they don't produce noradrenaline at all. And this results in a drug being imported from Japan called L-DOPS, which can be given by mouth and is converted into noradrenaline. This was in the late 80s, by the way, and it was 2014 before the FDA approved it, so these things do take time. So things were going very well, and the mid-80s, of course, almost Dickensian, you might say, plenty, and things could change, and one of which was that Roger took up the mastership at Pembroke College, but very fortunately continued with the work with 3 clinical sessions at Queen Square. In 1987, Stan retired, which was, again, a sad event, but a joyous event, particularly with the events which followed. And I'm going to show you one which has already been shown before, and I thank Jerry for providing the slides for this. You've seen this, so I'm not going to go over it again. But this was part of the meeting which Peter Sever and I organized, although it was streamlined, and Jerry, you're in the audience, thank you very much for streamlining it. It was serious stuff, but it was great reading, as I found, particularly the after-dinner speeches. David Graham Smith, for one, and Stan also, and you can be assured, as you can see from this slide, that he did regale us, I think, at the end of this. So we then got to the end of the 80s, and I made up my mind that maybe I'll take a chance because the specialty didn't exist. I would continue. And this is really now with discussion with Stan, who, although he'd left St Mary's and retired, he was still there because he would come in despite his commitments to the Wellcome Trust and the Hunterian Institute. And it was marvellous to talk with him and to get his advice, as it were. Thanks to him, a personal chair was awarded. He, Peter Richards, and David Marsden at Queen Square. So I had a joint chair between the two institutions. And it was really rather good that there was an increasing number, almost an exponential rise in the number of clinical referrals, and also, as a result, the research which could follow from that. We wondered why. This was for a number of reasons. One was that, again, Stan and Roger were very helpful in my starting the first clinical journal known as Clinical Autonomic Research, now the official journal of 3 societies, the UK, the American, and the European Society. And this, of course, spread the word. But, of course, this didn't necessarily result in referrals, clinical referrals, which were needed if you were going, because all the work was done in humans at the time, not at the time and continuously since. And I'll show you the problems and the advantages in having a number of referrals, but there are disadvantages too, as shown in this busy slide. And this indicates, if one can make this out, that there were about 250 in the mid-80s, and these were largely research studies. And this gradually grew, and one of the reasons we think was that you could now measure blood pressure continuously with a cuff with a finger, known as a Finapress at the time, or the phenometer. And they grew enormously, threefold in the mid-90s and almost tenfold later. Now, you would say that's advantageous, but it wasn't at the time because it posed practical problems. I was there on my own with a very good team, but a research team. We were very thin on the ground clinically, so how would one deal with this? And this is where, again, Stan came in terms of being, let's be innovative, he said. You see, you're not going to get doctors who are going to stay other than more than 3 years because they complete their MD, PhD, and then they go on to greater things as well. So why don't we train scientists, those with PhDs and with MSCs, who would do the testing, would be linked with the research, and they would be supported by biochemists, again, specifically, and autonomic nerve specialists. And this really made us, or enabled us, to continue with the work. Thanks to this, and it's flourishing still, so the training programs for this. Now, Stan also had an uncanny, and I use the word prescience in terms of how matters would evolve, and one of which was as we reached the end of the old millennium. And I'm going to skip this slide because I don't think that's really needed now. And this is how matters would, because I was having doubts myself as to how sustainable matters would be, as it were, looking at the next 10, 15 years. And he said, no, continue. And one of which was starting studies with functional autonomic brain imaging. This is with fMRI. And this was with Hugo Critchley, who was a key person on this, and Ray Dolan at Queen Square. So one can actually link up autonomic changes with what's happening within the brain as accurately as can be. He was also very interested in this disorder known as the postural tachycardia syndrome, where they look perfectly okay at the moment, they stand up, their blood pressure doesn't fall, but the heart rate rises markedly. And there were other reasons for that, other than the autonomic, and that is that it's linked with something called the Ehlers, which you all know well, I'm sure, a connective tissue condition, Ehlers-Danlos syndrome, and we now know that a number of them have multiple systems involved. And again, this was something which he found fascinating, because he was very much for spreading things across for an integrated approach, particularly clinically. A whole range of other things occurred, which I'll come to very briefly there. But in 2014, this is the year when I took, I suppose, partial retirement in a way, it was thought that the two units, this is one unit at St Mary's and one at Queen Square, would be far better if they amalgamated. And this is what's happened. It's amalgamated, and in fact there's now an established academic department with a chair at the Institute of Neurology and UCL. Now, a lot has flowed since then, thanks to the excellent people who are working there, and with a bit of help from my end peripherally. This is looking at body-mind autonomic interactions and anxiety, causing anxiety, and autism, now a big area as well. Autoimmune-mediated autonomic impairment. These were studies, these were samples that we collected, and again, thanks to his guidance, in the mid-80s with some of the patients. But they weren't the assays at the time, and now the linkage with Angela Vincent and others, one could analyze the antibodies and use treatment to help. So this was one of the first disease-modifying treatments. Most of the others were either replacing or helping with the symptoms. And I'm sure he'd have been particularly interested in what would be happening, because it's been suggested that in some with long COVID-19, autonomic dysfunction may be involved, and this is being approached at the moment. So on that, ladies and gentlemen, I'd really like to end with this picture, and I'm really very glad, and thank you, Celia, for forwarding it to me. This was taken in 1982. It was a particularly pleasing time for me because I was appointed as a consultant to work with Stan, by Stan, to work with him. So quite an achievement, I thought, for somebody like me, at any rate. And this was taken at Christmas time. There used to be a Christmas lunch, largely. Stan would do the carving at the time. We still haven't discovered who the sister was, unless somebody can come up with it. And this leads me to thanking various people. And this includes, of course, the many patients over the years. Without them, we'd never been able to move forward in this field. The various people in the units, both at St Mary's, Queen Square, the institutions, and in London and abroad, all of whom have actually worked together in having the field move forward. This is my wife, Lindy, and our eldest, Sarah, and James, at the time. And again, she's played an important role over the last 45 years. But the key person here is Stan. And Stan, as always, was amazing in terms of the diversity of what he could provide. He was clearly the super clinician, as you heard. He was a scientist, and not just in one field, as a physiologist, as a pharmacologist, on the biochemical side. But importantly, he interspersed this with humor, with mirth, with joie de vivre, and he kept us in laughter at the time. And that is really quite a quality which is much appreciated by all of us. So thank you very much, ladies and gentlemen. And I just end, I really think that he is one of the key factors with key persons with Dorothy Bannister in terms of the development of clinical autonomic neuroscience and in clinical autonomic medicine now becoming a specialty. So thank you very much for listening.
Thanks very much, Chris. Excellent, excellent. We'll take questions at the end of the session, and it's now a great privilege to welcome back Stafford Lightman. I remember Stafford on the unit at Mary's as one of the tasks that he was charged with was to measure the levels of renin and aldosterone throughout the 24-hour period. And so he was one of the few people who would be in the unit day and night. And he taught me two things about 24-hour profiles. The first one was the difference between nictemeral rhythms and diurnal rhythms, and I confess I can't remember what it was that he taught me that was the difference, but he'll probably tell you. But the second thing, which was hugely important to a clinician, was that having looked at those traces, 24-hour traces of aldosterone going up and down and up and down and up and down, and renin going up and down and up and down and up and down, was that when you're in the clinic and you take a blood sample from a patient and you see a level of aldosterone of 300 nanograms per mil or whatever it is, you know it is completely unrepresentative of what that patient's profile is. And for years and years and years and years now, people have said to me, why isn't the aldosterone raised in hyperaldosteronism? And no one actually went back to some of the original data which Stafford published to show that if you stick a needle at one moment in time and think that that's some representation of the 24-hour profile, it obviously isn't. So perhaps you'll tell me the answer to the first question, Stafford, but welcome, and we look forward to your talk.
Well, thank you very much for that introduction. I'd first of all just like to say how grateful I am to be invited to this meeting, David, Peter, and the Peart family. What's totally amazing to me is just coming here today is the huge group of people that Stan attracted to work with him. Nowadays, you know, if anyone appoints someone to their department, they have to be working in exactly the same area to forward that individual's research. Stan wasn't like that. He appointed people that he thought were interesting and might have potential. And it created this fantastic atmosphere, which I've certainly never experienced in any other department that I've ever worked in. In fact, it was really quite interesting because Stan actually appointed me after a particular very senior colleague in my own area I'd been to see about a job who told me that he didn't want to appoint me because I was just a dilettante. And I haven't met this guy for a bit since, but Stan took me on. I mean, I met Stan. The first time I met him, I went to his little office and he appeared, he came by motorbike, he came in, he'd had his motorbike helmet on. I wasn't actually quite sure it's him, but I noticed he had a bow tie on and I knew Stan wore a bow tie, and so I presumed it was the right person. Anyway, he took me on despite the fact my interests were extremely different from his. But we did have a little bit in common in terms of research interest. And what we had in common was this gland here, the adrenal cortex. And you've already heard about the fantastic work that Stan did to create our understanding of the renin-angiotensin system and its regulation of aldosterone. My interest was coming down from the other end, and I was more interested in cortisol, which is secreted by the same gland. And I was, as Peter has very kindly introduced me, interested in rhythms of hormones which continue throughout the day. And the master clock for this is the suprachiasmatic nucleus in the hypothalamus, which gives you a 24-hour rhythm of the peptide corticotrophin-releasing hormone. This acts on the pituitary to give you a 24-hour rhythm of ACTH, which acts on the adrenal to produce cortisol. Now, the interesting thing is that if this was the only thing controlling the levels of cortisol, what you would expect is this. You would expect the levels of cortisol to go up early in the morning and slowly decrease throughout the rest of the day. But actually, if you take multiple samples from one individual rather than meaning lots of people, what you see is this. You see this fantastically pulsatile secretion of cortisol, which continues throughout the whole day. And interestingly, this is found in all animals or all mammals in which it's been tested. Obviously, the rat being nocturnal, the major amount happens during the night, and in humans, the major amount in the day. I want to point out that these peaks start in the middle of the night. It's not when you wake up and get up. These peaks actually start here in the middle of the night. So you've got this daily rhythm, but underneath that you've got this ultradian rhythm, and these rhythms are very, very marked. And what I just point out is in the morning here, if you take a sample of cortisol from a patient, and then you might take another one 30 minutes later, they might be 100% different from each other. They might be completely different, simply because of this rhythm, which is why the normal range is completely meaningless about that time of day. And I won't go through it in great detail here, but we were really interested in this. And like Stan always did, he was very interested in working with mathematicians. I also worked with mathematicians. And we tried to work out what the cause of this ultradian rhythmicity was. And it's really interesting because we thought to begin with it must be something happening in the hypothalamus, but actually it isn't. It's all down to the adrenal gland. And the reason is that the adrenal gland cannot store cortisol. Because it's so lipophilic, you can't store it in granules. So every time you secrete cortisol, you have to newly synthesize it. Why is that relevant? Well, the relevance is that the pituitary makes ACTH, it hits the adrenal, and then there's a delay. And there's a delay of, say, 15 or 20 minutes before the adrenal gland can make cortisol, and it feeds back and turns off the pituitary. Mathematically, any feed-forward, feedback system with a delay, or at least one delay in it, has to oscillate. It has no choice. It just has to oscillate. And we did, after the mathematical modeling, we did biological testing, and we proved that we actually had a sub-hypothalamic oscillator, which caused these pulses of cortisol. The next thing was to see whether or not these pulses of cortisol were relevant and what happened at a signaling level. So what cortisol does is it goes around the body, it goes into cells, it binds to one of two types of receptors, either the glucocorticoid receptor or the mineralocorticoid receptors. These translocate into the nucleus, and they dimerize, either homodimerize or they heterodimerize, and then they bind to glucocorticoid response elements on the gene, and transcription takes place. Now, we wanted to look about whether this was actually happening, so we first started very simply in cell culture. And what we did, and I'll just show you the model we looked at, is we had cells with no cortisol in, we gave a pulse, we washed it out, we gave another pulse, we washed it out, we gave another pulse. And the glucocorticoid receptors, we bound to green fluorescent proteins, so all the glucocorticoid receptors are green, and you can see they're mainly in the cytoplasm. The first pulse we give, it all goes into the nucleus, and these particular cells we engineered so they had lots, about 2,000 glucocorticoid response elements all next to each other, so we can actually see the glucocorticoid receptor bound to the DNA. We then washed the cortisol off. The receptors stayed in the nucleus, but they came off the DNA. The next pulse, they bound again. We washed it, it came off, and we put it on, and it came on again. So you could see pulsatility of the binding of the glucocorticoid receptor to DNA. We're also interested, of course, in the mineralocorticoid receptor, and so this is just one cycle here to remind you the glucocorticoid receptor goes from the cytoplasm into the nucleus, it binds, you wash it off, and it disappears. The mineralocorticoid receptor, which is with M cherry here, so it's actually red, it goes from the cytoplasm into the nucleus, it binds to these same GREs, but it doesn't wash off. The dynamics are completely different, and so what we're basically seeing is we're getting pulses of cortisol in the blood. At the peak of each pulse, you've got the glucocorticoid receptors and the mineralocorticoid receptors bound to the DNA, and as you wash it off, the glucocorticoid receptors come off and the mineralocorticoid receptors remain bound. These were studies that we did in cell culture, but it also happens in vivo. So here we're looking at a rat, and the rat's adrenalectomized. We infuse pulses of corticosteroid into the rat, that's in green. We then take the hippocampus up and look at the binding of the glucocorticoid receptor to the DNA. So you've got pulses of binding of the glucocorticoid receptor to the DNA. And then we look at transcription, and here we're looking at transcription of a particular gene, heteronuclear RNA of period 1 gene. So you can actually see gene pulsing with every single pulse of glucocorticoid in the plasma. So I'm going to jump on now. I'm going to jump forward, because this sort of brings me back to work that I originally did with Stan such a long time ago. I was really interested, as Peter has told you, in rhythms that happen across the day. One of the things that I found very frustrating is that basically you had to bring people into hospital, you had to stick needles into them, you had to keep taking blood samples from them, and when you did it at night you tended to wake them up, which caused a problem. It was very expensive and it was very difficult. And I wanted to find a way of being able to sample patients at home, going to work, doing their normal everyday activity. So what we delivered, what we actually came up with was a system of microdialysis. And I'll show you this in a bit more detail, but basically there's a pump, you pour, saline goes in, and you put just under the skin a microdialysis membrane. And so cortisol in the tissues goes into the microdialysis fluid, which is flowing through, and then it comes out into a collector, and you can collect it here. So just to show you basically what it is, there's a pump which pumps it in. We put this under the skin. It's painless. We used to use local anesthetic, but we don't anymore because it's actually much less painful not to give local anesthetic. And then this is what we made, this specialist collector, which can collect timed samples which are happening throughout the day. And when we do this, we can look at what happens in the tissue, and we can actually measure the whole steroidome. But coming back to Stan, I really wanted to show you that I have come back to looking at aldosterone, which was not something that I used to do. So this is microdialysis in a subject who's just gone home and come back 24 hours later. In the red, I can show his cortisol here, and so this is his sleep time here, and as you'll see at about 2 to 3 in the morning, there's this huge pulse of cortisol, which we always expect. The interesting thing is, if you look at his aldosterone, you've got these lovely pulses of aldosterone happening all the time. But there is no relationship between cortisol and aldosterone at all until the morning. And always in the morning, when you've got this ACTH-dependent pulse of cortisol, you get this big pulse of aldosterone. So this is just one subject. This is another subject. You'll see these lovely pulses of aldosterone here. And you'll see that when you have this pulse of cortisol in the morning, you have a pulse of aldosterone. But during the day, the relationship between cortisol and aldosterone is lost, presumably related to renin-angiotensin, but here it seems to be more dominant. Now, one of the things Stan was really interested in was in Conn syndrome, where he was sure that there was a changed sensitivity of the Conn's tumor to ACTH. So we've been looking in patients with primary hyperaldosteronism. So these people have got a little benign tumor in their adrenal cortex, which makes aldosterone. And the median of all our normal subjects here is blue, so that's the median in normal subjects. In red is this one subject. You'll see these huge pulses of aldosterone. And so, as you say, if you took a blood sample there, it would be normal. But you take it 30 minutes later, it's miles up here. It's fantastically pulsatile. But what's really interesting is if you look at aldosterone and cortisol, every pulse of cortisol has a pulse of aldosterone. That's a pulse of cortisol here, a pulse of aldosterone, pulse of cortisol, pulse of aldosterone. They follow each other absolutely throughout the whole day. And here's another patient, so this is just his absolute levels of aldosterone throughout the 24 hours. And you can see the aldosterone is following cortisol. So these Conn's tumors have lost their normal response to renin-angiotensin, but have become very, very responsive to
to ACTH. And this is just one other primary hyperaldosteronism. You'll see these huge levels, but at some times of day they're quite normal. This huge rise in the morning, and again, if you compare cortisol and aldosterone, they follow each other. So I've come back to where Stan took me right when I first worked with him, which was looking at the regulation of aldosterone. And basically, from the work that I've been doing, what we have been able to show, and this was all stimulated originally by working with Stan, was that cortisol and aldosterone are secreted with both circadian and ultradian oscillations. Each ultradian oscillation of cortisol is associated with episodic GR activation, whilst the mineralocorticoid receptor remains occupied between pulses. We've shown that we can have automated ambulatory microdialysis allows us to do dynamic sampling across the 24 hours without blood removal. And I say we can now measure lots of things. We can measure catecholamines, we can measure the whole metabolome, all through this particular system. There's concurrent, presumably ACTH-dependent early morning peak of both cortisol and aldosterone in normal people, and in Conn's adenomas seems to retain ACTH responsiveness across the day, and we're still going through this data at the moment. I haven't had time to talk about it, but we've also shown that the ultradian pattern of glucocorticoid secretion determines tissue-specific genomic responses to cortisol, and pulsatile cortisol secretion affects your clock genes, it affects the way you sleep, your sleep and activity cycles. It affects your memory. It's very important for memory. And if you don't have the pulses, your memory isn't so good, your emotional response and your brain connectivity. And the most important thing is to say, thank you, Stan, for encouraging me to follow my own interests. You know, my interests were quite different from other people on the unit. They fitted very nicely. But Stan was happy to take on this person coming from a completely different area and allow him to work in his unit, and allowing me to develop things that I was interested in, and I shall always be extremely grateful to him for that. I've never worked in such a great department in my whole life, and thank you, Stan.
Well, thanks very much, Stafford. We now change tack a bit. And I'm grateful to Jonathan Weber for pointing out to David and me many months ago when we were actually putting together the program for the first symposium, which was delayed because of COVID, that there were two scientists, clinician scientists, who subsequently had stellar careers in the field of immunology that were Mary's graduates. And as Jonathan pointed out, it would be very surprising if Stan had not had some influence very early on in their careers, if only pointing them in the right direction. Now, I don't know what that contact was, and I'm sure individually they'll tell us, but it's a great pleasure to welcome the first of our two immunologists, Alan Townsend, to talk to us about adventures in immunology. Alan.
Well, thank you, Peter, and thanks very much for inviting me to this. I thought I would actually just talk to you and tell you a story rather than show you any slides, because I didn't think you wanted an immunology seminar this afternoon. I'll give you a few sort of pictorial descriptions, but I thought it would be the most appropriate thing to describe the effect that Stan had on a medical student, a pretty sort of idealistic, immature, probably, young medical student who arrived on the wards, having come to Mary's as a preclinical student, being congratulated on my A-level results, and very narrowly managed to avoid being booted out after 2 years because I failed second MB. But I won't go into the details on that. But the clinical course started And my first firm was Tommy Kemp, which was very enjoyable. But he said, you must go to Stan's open teaching sessions, which were twice a week in the lecture theatre with a patient, and you'll learn something. And I went to the first of these and was just immediately hooked. The whole atmosphere that Stan created with the patient, thoroughly involving the patient from the very beginning, and in fact later on when I had to choose patients for him to demonstrate on, they loved these sessions. They'd come back absolutely fizzing with enthusiasm about the professor with the dicky bow. And I think studies have been done actually to show that bedside teaching of one form or another is actually very enjoyable for patients mostly, if done appropriately. Anyway, these were of two kinds, if you remember. There was the one where he took a normal history and did a physical examination and then reasoned with that information and then predicted all the blood tests and so on. But the other was sheer wonderful theatre. It was when he explained to the patient very carefully, and this was very important, was one of his teaching points, was how to explain that you're going to do something rather odd with a patient, to the patient, and involve them, that he was going to examine them carefully, find all the clinical signs, and then reason backwards and describe what the history would likely to have been, and then also he used to predict all the blood tests, which I found absolutely extraordinary, and this was a real sort of Sherlock Holmes bit of theatre, obviously, but absolutely terrific. Now, in some of these sessions, Stan mentioned various great scientists, such as Claude Bernard, I remember, and that name stuck in my head. And I was later editing the Gazette, and I was trying to get people consultants to write for the Gazette. And this was mostly profoundly unsuccessful, I should say. But one of the people I went to was Professor Dudley, the professor of surgery. You remember, Stan and he had an interesting relationship, I should say. And I thought it would be interesting if Professor Dudley would write something about Zachary Coates' acute abdomen in rhyme. I thought this might be an opportunity for some little, amusing. Anyway, I was disabused of this notion very rapidly when he told me that he thought it was absolute rubbish and he wouldn't waste his time on such a project. So I backed out of the office. I felt a bit like Tintin in front of a performance by Bianca Castafiore, the hair being whisked back. And but as I got out the door, he said, "But I will write you an essay on a book of my own choice." Anyway, a few weeks later, this essay arrived on Claude Bernard, and it was an analysis of his book, The Introduction to the Study of Experimental Medicine. It was beautifully written, and a lot of quotes from the book, which I later found he couldn't find a copy, so these were from memory, and they were virtually word perfect. So he had a fantastic memory. But it was a brilliant essay, and I then later read the book. And I must say that gave me, as it were, an epiphany, what you might call a moment of sudden and great revelation or realization, because now I knew that I wanted to be a doctor like Stan Peart, and I wanted to be a scientist like Claude Bernard. So I got the house job with Stan, and that was, of course, a revelation. Stan's ward rounds were extraordinary. But luckily, in those days, one had time for long ward rounds, and some of them were very long indeed, you will remember. But a patient's condition would be analysed to the point, as I felt it, it was the absolute limit of all knowledge. There was no further place to go except questions. And this was also an inspiration. I remember the Christmas on the ward with him coming in and carving the turkey. One year it would be a dunce suit, other year it would be a Superman suit, with all the patients sitting round and having a thoroughly good time. So I knew what I wanted to do, roughly speaking, in terms of what I wanted, the kind of thing I wanted to do, but I had no idea what subject. And so I applied for the SHO job in neurology, which was a combination, remember, of neurology, VD, inpatient VD, dermatology, and you're on the cardiac arrest rota. And very important, you were Cocky Coburn's house physician. Now, Cocky was a tremendous character and actually a brilliant doctor. But I remember very much at the interview for that job, Cocky was sitting at the interview panel with Stan and my later father-in-law, and he had this quizzical expression, which was, you know, he used to sort of cock his head on one side and didn't ask any questions. And I was sitting outside afterwards waiting to know if one was going to be recalled, and he came out, clocked his head on one side and just wiggled his finger at me, and I came up and he said, very serious, it was Townsend, I think I've got to warn you, if you're not very careful, you're going to get this job. And it was a typical Cocky interaction. I could describe many more. As I say, he was a brilliant doctor, and I think the next one I remember most was when we went to see a medical student in Wilson House who'd been very ill after having a sore throat, and Cocky said to him, "Stick your tongue out." And then he looked at me and says, "Does that remind you of anything?" And he had scarlet fever. So as I say, I didn't know what I wanted to do, but the great thing about this job was that it gave you time, because although it was very busy in the daytime, we didn't do take medicine at night. So if everything was quiet, you had time to read. And one thing I was seeing were patients with HLA-associated diseases. So, you know, some of the VD patients, and we had MS patients on the ward, and recently HLA-DR3 had been associated, I think, with MS, and I was wondering why, you know. And there was a wonderful essay at the time written by Peter Medawar where he had pointed out that the HLA system had not been created simply to cause trouble to transplant surgeons, but nobody knew really what it did. And then gradually, as these disease associations cropped up, there was obviously something very interesting going on. And then in 1974, there was a critical paper from two characters called Zinkernagel and Doherty, who were quite young at the time, working in Australia, and they spotted that the recognition of virus antigens on infected cells by T lymphocytes depended on the HLA system. So they only recognized the antigens in association with HLA. And in fact, later in a series of absolutely stunning experiments, they showed that it was in fact the thymus in which the T cells had grown up in was the key thing that taught the T cells how to recognize their HLA molecules. But there was still a huge question about what they were recognizing. Nobody knew what the antigens in the viruses were. So Stan would call me into his office every now and again and saying, "What's your thinking? What are you doing?" And I explained all this. And he said, well, you need to go and see Ita Askenaz and John Skehel at the National Institute. And he'd met Ita many years before. She was a biochemist then, but she'd become an immunologist. And John Skehel was a brilliant virologist who, at the time, besides working out the structure of the main hemagglutinin of the molecule, of the virus, was the chairman of the committee, the WHO committee that organizes which strains of flu go into the vaccine. And in the NIMR freezers, there was every strain of flu that had been isolated from humans since 1933. So there was a lot to choose from and a lot of nice variation in there. And that day was a day in October. I can remember it very well. It was an absolute inspiration. And it was quite obvious that flu, if you wanted to learn about T cells, the influenza virus was the thing to study. Not only was it a huge clinical problem, but it was a perfect model organism with 8 RNA segments that encoded only 8 to 10 proteins. And this maybe would help me define the question that I'd set myself, which is what do the T cells see, but how to do it. This was where things, I'd often heard Stan talk about serendipity, but serendipity is in fact incredibly important, and you've got to be ready for it, because if you don't, it'll pass you and then you'll lose it. And I had a bit of serendipity. So while working at Mill Hill with Ita, we couldn't work out what the antigens were, and the reason for that was that most T cells see something that's common to all influenza A viruses. So all this variation was all very well, but it didn't help us define what the T cells recognized. There was no molecular biology at the time, there were antibodies to these various proteins, but if you put them in the reactions with the T cells, they didn't do anything. So it was very difficult. So I decided to study the HLA molecule. And there was mouse strains in which the HLA varied just by one amino acid or two amino acids. And you could then, with these nice T cell clones that we'd isolated, start to work out how variable the recognition was and so on. This was in the days before there was any T cell receptor knowledge or anything of that kind, no cDNAs and so on. And that turned out to be very lucky, because the mouse strain that one had to use to do those studies is really the only mouse strain that does make T cells that can distinguish one influenza A virus from another at high frequency. And I'd done all these studies it took about 18 months to do this work. It was actually quite difficult, and to show that T cells did vary a bit in how they recognize the HLA molecule. And right at the end, I thought I'd better check the parental viruses of the strains that we used as a kind of finishing off experiment. And it turned out that they all recognized just one and not the other. And not only that, but they recognized the one that was encoding the molecules that were inside the cell, not on the cell surface. And at the time, we assumed that the T cell had to interact surface to surface, and that it would be one of the surface proteins, of which there are only two, the hemagglutinin and neuraminidase. So I got incredibly excited about this. I thought this is just what Claude Bernard would have gone for, you know, and it was not what you'd expect. Absolutely wonderful stuff. And I went down to see John Skahel that evening. So we used to go down and visit his office, and then we'd go for a drink in the bar. And he looked at these results, and he looked at me, and he said, well, it's obvious. You muddled the tubes. Which, of course, could easily have been, because I had 3 viruses. You know, you got... So, but rather deflated, I worked with Rose, who was his technician, to grow up fresh stocks from the freezer, originals, and did it all again, many times, actually. And it was absolutely clear that what was being recognized was not on the cell surface. Now, this was impossible. What was the biochemistry of this? There was no known biochemistry that would explain it. But I, partly from the sort of Claude Bernard influence, and partly by talking to Stan and said, hold on to it, you know, don't let it go. I carried on working on it. And very soon, there were ways of distinguishing what the genes were that were involved, because technology, it was evolving very rapidly. And a group in the States, Peter Polizzi, had worked out a method to identify the RNA segments in each individual virus. And this mapped them to the nuclear protein. That was even more strange, because the nuclear protein's in the nucleus, nowhere near the cell surface. Shouldn't be on the cell surface at all. But then molecular biology came along, and one could put one gene at a time into cells and chop the gene up and express just little bits and so on. And what became obvious was that you could express very small bits. They were very rapidly degraded and destroyed inside the cells. And it seemed that the more rapidly degraded they were, the better the recognition. And to cut a long story short, and this carried on for 14 years of hard work, and many different groups coming in and joining in, and working with Andrew by this time on human T cells that behaved in the same way, that these proteins that fall off the ribosome, they get degraded very rapidly. There's a special mechanism that takes small peptides and shunts them into the endoplasmic reticulum, where they bind into a groove in the HLA molecule, all of which has been beautifully crystallized now and shown. And then that moves up to the cell surface, and that's recognized by the T cell. And it's happening all the time in all of your cells. It applies to all of your cellular proteins, not just new ones from outside, and to mutated proteins and oncofetal proteins and somatically mutated proteins. So, for instance, in some tumors, this is really important. And in melanoma, about 25% of people now are treated using these principles to destroy, specifically destroy melanoma cells. So it is having applications, and gradually it's having applications in vaccinology. So by 1994, I had fulfilled to some extent one of these 2 ambitions, but the other ambition I had very much failed at. Had not seen a patient for 14 years, and I did miss it. And so I went to the professor of medicine in Oxford, David Weatherall. I think he was still, yes, he actually, I think may have just retired or was about to retire. But anyway, I went to see him and said, what do you think? And he looked at me as though I was completely mad, of course, but smiled and said fine, because in those days there was no, I could have just gone straight back on the wards, there were no special rules, didn't have to retrain in any way formally. So I did, I just went back, and I decided to go back exactly at the level I'd left off as an SHO. So I worked for 2 years as an SHO and then 2 years as a registrar, and I worked with Howell Jones, you may remember, who had been a registrar at Mary's, I think. I felt at that stage, having worked with most of the consultants, that he was the best general physician with Simon Winner, very, very happily for 6 years, while keeping the lab ticking, obviously, but it was pretty well ticking. And then I had my own illness, which I won't go into, but I was pretty ill for 6 months, and very unpleasant. And at the end of that, the European Working Directive had arrived, and that made life very different on the wards for us. So I decided to get back in the lab, which I have been doing ever since, very, very enjoyably. But all of that time, I was teaching a lot. We're doing a lot of clinical teaching, and I set up clinical teaching based on colleges in Oxford, which had not been done, strangely. But of course, if you teach a group of students for 3 years, it's very enjoyable because you get to know them. And throughout all this, I thought of Stan very, very often, both in my scientific work and in the clinical work. And so Stan, I can say, had a profound and lasting effect on the way I tried to practice medicine and do science, for which I'm very grateful.
Thank you, Alan. I have bad dreams sometimes about finding myself back as a houseman or as a casualty officer 40 years after I was last on the wards, and the thought now of going back and becoming a houseman again or an SHO fills me with absolute sort of trepidation. Anyhow, I'm delighted to introduce the next immunologist, Andrew McMichael. Andy and I were contemporaries at Cambridge before we went to Mary's. We graduated at the same time. I became a pharmacologist, but Andrew won the pharmacology prize in the final year, much to my distress. But anyhow, Andy, we look forward to what you've got to say.
Good. Well, thank you. And it's a great privilege and honour to be able to speak at this symposium. And thank you to Peter and David and the Peart family for the invitation. So I'm going to tell you a bit about my venture in immunology, which was triggered by Stan, and I'll explain how. And this goes back exactly 50 years to 1971. And 1971 looked a bit like this, and probably there are people in this room who remember it. Usually when I speak, nobody remembers it. It's like a different planet. But these are various things that were going on, but in the middle, my first daughter was born, and my wife Kate's first daughter, Fiona, was born. And this is relevant because in February of that year, I just passed membership, and I was looking around for jobs and wasn't quite sure what to do. And I went one Monday afternoon to the antenatal clinic to pick Kate up from the clinic, and Monday afternoon was Stan Peart's medical outpatients, and as I was walking up the stairs, I bumped into him literally walking down the stairs, and I'd obviously known him a little bit as a medical student, but at that sort of level previously. But he stopped me and he said, well, how are you getting on? Nice to see you. What are you doing? So apart from visiting my wife, he said, I said, well, I was wondering what to do next. And so he said, well, are you interested in going into science and doing some laboratory research? And I said, well, yes, I was actually. And he said, what are you interested in? I said, well, I thought immunology was interesting, and I knew absolutely nothing about it, really. And he said, well, come and see me. And A couple of days later, at 7:30 in the morning, I went up to his office in some warren at the top of the hospital. And he said, you should go and see my friend Ita Askanas at Mill Hill. And actually, she was his neighbour and contemporary as well. And obviously, they'd known each other when Stan was at Mill Hill. So that's where I went to see her. There she is. And she was senior scientist in immunology and later became head of the immunology group at Mill Hill. And here is Mill Hill. We've already seen a picture of it. Sadly, I think now being demolished or has been demolished. But this was a fantastic place to go. And so I went there to the lab. And the lab was a very different place then from what it is now. And you don't have to read all of these, but basically we didn't have a lot to play with at that time. Most things were done in mice, as Alan just mentioned. We didn't have monoclonal antibodies, so we used the Institute goat to make antibodies for us. And goats have a fabulously big jugular vein that you can stick cannulas into and get large amounts of blood, and they don't seem to mind at all. And so you get large amounts of blood and you can purify antibodies out of them. And goat antibodies and rabbit antibodies were our sort of bread and butter for antibodies. And then we had all these various techniques, mostly in vivo experiments, but a few simple in vitro experiments and some rather basic now immunochemistry. What we didn't have are all these things that are now sort of standard stuff of cloning cells, cloning DNA, sequencing, etc., imaging, proteomics, and so forth. But notably, we didn't really have proper computer. Well, there were computers, but they were about the same size as the Institute. And we didn't have anything on the laptop except simple machines that could just add, subtract, divide, and multiply. And we certainly didn't have smartphones. On the sort of more positive side, in some ways, we have much less paperwork to deal with. And although these things are all very worthy and important, they do take a lot of our time now. But in those days, there was virtually nothing. We did have to have an animal license, but it was very simple to get. Ethics was sort of dealt with by discussion among groups. And that was about a bit, none of the other stuff. There was no security. Anyone could just walk into the institute and go and see anybody, which was rather nice. Nowadays, you have to almost have a passport to get in. You probably have to have a vaccine passport now. Interestingly, there were none of these, which of course have two of them, HIV and SARS, are currently occupying my remaining research time. And of course, they have been had a major impact on medicine and infectious disease, as everyone knows. The immunology itself was all about phenomena. So there were these things called adjuvants. You suck some mineral oil and kill mycobacteria in with your protein, nice pure protein, sort of messy adjuvant, and you got an immune response. If you didn't put the adjuvant in, you didn't get very much. There were all sorts of cell types being rather poorly defined. There was some basic genetics beginning to come out. There was, as Alan mentioned, this HLA or MHC restriction. Every experiment, there was a lot of background noise going on. There were various factors people were claiming, but half of us didn't believe. But actually, the people who were doing all this were really good, most of them. And people like John Humphrey and Av Mitchison and Ita herself and many others were actually very carefully sorting out these phenomena. And in due course, they all had molecular explanations. So we know the adjuvants are pattern recognition stimulators. They're being recognized by particular receptors. They're stimulating interferon pathways, etc. And these have all been worked out. They've won a number of Nobel Prizes along the way, and they're all real, and they all have molecular explanations. So the difficulty with immunology that a lot of people have, and I had, it took me ages to understand anything, was what were all these phenomena about, now you have molecular explanations. It's much simpler, although sometimes the molecular explanation is amazingly complicated. So, sort of stimulated by Stan to get into this and to go into the basic science, I moved from Mill Hill to Stanford and then to various institutes in Oxford, and became interested in, like Alan, HLA molecules, also triggered by the disease associations, particularly the B27 and ankylosing spondylitis, which is still not fully understood. The genetics of HLA molecules, their structure and their functions, T-cell immune responses to viruses, which seem to me to be likely to be very important clinically and for vaccines. Working on influenza initially, then as HIV came in, HIV, and recently done a little work on SARS coronavirus 2. And also a little bit of work in innate immunity, which also involves the HLA molecules. Stan didn't have any direct interest in immunology, except perhaps in the transplant context, as we heard earlier. But I know from sitting on committees with him at the Wellcome Trust that he knew something about everything and he could assess something incredibly quickly. And he had this wonderful method of assessing a proposal that he would have read them all as the chair of the committee. And he'd pick one up from the table like this. And if he liked it, he'd sort of hold it here and we'd discuss it. If he didn't like it, he'd hold it here, and he was about to drop it into an ever-increasing pile of discarded proposals. And your job as a committee member was to try and save it. And occasionally it would go in this direction. More often than not, it would land up on the floor. But he was right. He was always right that he had this wonderful way of being able to assess science in other areas, whether the ideas were good, whether the proposal was good, whether the plans were good, etc. So he could assess immunology, actually, and he knew who were good people to send people to go and work with. So I'll just tell you a little bit more about my own adventure recently. So I got interested in HLA-E in about 1998 with a fantastically good French postdoc. And HLA is a bit different from the regular HLA molecules. It's not polymorphic. It's very highly conserved. And it's conserved, I think, because it binds just one peptide, which has that sequence, which actually comes from the signal region of classical HLA molecules, which are the highly variable ones. But these signal peptides, they all contain these 9 amino acids, which are there's a tiny bit of polymorphism here, but basically the same thing. This binds very well to HLA-E, and then it interacts with this particular receptor, NKG2A, on CD94, on natural killer cells and a few CD8 T cells. And it regulates their function. So NKG2A, which is the dominant one, suppresses the function of the NK cell. And what that means is if a cell is lacking HLA classical molecules, the variable ones, which happens with a number of viruses and in some cancers, that inhibition of NK cells doesn't happen, and the NK cell can then kill the target cell. And this appears to be really important because, and I say that partly because HLA-E is so conserved. There's purifying selection, basically, that has preserved this molecule and indeed that particular sequence as a pair to have this function. So in 1999 or 2000, when we published all that, I thought, well, that was solved. However, it then turned out that sometimes HLA-E could present peptides to T cells, like Alan described. And indeed, Alan discovered originally, as he told you. In this particular experiment, I'd become interested in HIV vaccines, and an American called Louis Picker had tried to stimulate T-cell responses with a vaccine based on cytomegalovirus as a vector. So this is a monkey cytomegalovirus. You can put some SIV, which is the monkey HIV, into it and infect monkeys with this. They actually then get a persisting infection, but it stimulates a massive CD8 T cell or killer T cell response. And when he challenged these monkeys with SIV to see if they could be protected, 50% of them, those shown in red, actually become infected, but they then completely clear the infection. So when you test out here, there is 0 virus in these monkeys, even though they were infected. The other half seem to behave like the controls, and we don't know the difference exactly between the two. But the amazing thing is, to me, is that these T cell responses that do this are all involve HLA-E presenting peptides, not the normal HLA molecules, the HLA-E molecules. If we look at the function of HLA-E, this was the primary function I just mentioned. This one is the secondary function, behaving like a classical MHC molecule, as Alan discovered, presenting virus peptides as seen by the killer cells, the CD8 T cells. However, if you look how the peptides are that binding to HLA-E molecules, this is in a ELISA binding assay, the signal peptide is always the best, highest affinity binder. And the peptides that stimulate T cell responses are, with one or two exceptions, that's TB1 that's quite a good binder. And there's one SARS coronavirus one that's quite a good binder, but almost all the others are weak binders. Some of them are undetectable, and we've tested hundreds of these. So this is always best. These are second best. And there's a structural basis for that. If you look at the crystal structures, which are these, not the dots, this sort of thing underneath, this is the signal peptide bound to HLA-E in a crystal that we determined some time ago. These are some of these other peptides that are seen by T cells, so the non-signal peptides. They have the same kind of general structure, but if you look by this technique called small angle X-ray scatter, from which you can get a low affinity, low resolution structural model shown in these dots called a DAMIF model, whereas this one fits exactly. This one, the good binding peptide binds, looks pretty good. These other ones are a looser structure, so there's a more open structure, maybe more than one structure actually, with these other peptides. Although, if you keep the peptide around in high concentration, it contracts down and becomes very like the tight model. So, and this actually fits with the affinity. The smallest structure, this is the volume, are the high affinity binders. The loosest structure are the low affinity binders. So can you really get T cells that see these very low affinity binding peptides? And if we take one of these, one of the HIV peptides here, and we primed T cells in vitro, because we don't have a cytomegalovirus vaccine to give to humans, but we've primed human T cells in vitro, and we then cloned the T cells. We then took their receptor. This is what you can do nowadays. You clone the T cells, you take out their receptors, you put their receptors, so they're immortalized now as genes, the two chains. And they're then put into a third-party CD8 T cells. So this is like they do sometimes for cancer therapies. And put those T cells in with HIV-infected cells, you can see them killing the infected cells. So these are CD4 T cells. This is measuring P24 HIV GAG in this axis, and CD4, the receptor, in that axis. And normally when you infect cells with HIV, they become P24 positive and they downregulate CD4. If you put in an irrelevant T cell receptor into these CD8 T cells, you get the same result as the no-added T cells. If you put in a positive control, this is a classical T cell seeing HLA-B27 and a different GAG peptide, you completely wipe out the infected cells. If you put in the HLA-E-restricted T-cell receptors, we've tested 2 of them, you greatly reduce the number of infected cells compared to the control. So these T-cells and T-cell receptors are killing HIV-infected cells presenting these particular peptides. And this is a number of different experiments, just the sort of percent inhibition being shown. These are the 2 HLA-E clones. This is the B27 positive control, but of course it only works if the target cell has B27. If it doesn't have B27, you get nothing. So if you were wanting something for therapies, this would be very limited, whereas this one would actually work in everybody because everybody has the same HLA-E. So this second function of HLA-E might be quite useful. So that's what we're getting excited about now, and maybe they could be used in strategies to eradicate or cure HIV in patients, and we're still trying to work on that. And they may have applications in other areas, including in cancers. So all of this was triggered by Stan and that chance meeting in the outpatients at St Mary's, and I think I probably would have ended up as an endocrinologist because that was where my clinical training was heading at that time. But instead, he sent me to Mill Hill. He took a great interest in what I was doing. He connected me to a fantastic scientist, Dieter Askenas. And as I moved on to Oxford, he encouraged me to go there. He didn't try and bring me back to his own group or anything. And he followed what I was doing. And he actually sent Alan Townsend in my direction later. And he sent 1 or 2 others in my direction as well. And he was just a fantastically generous mentor, friend, and stimulator of scientific research. And he could pick out people wanting to do interesting things and support them, even if their interests were a little bit different from his. So I'm greatly indebted to him and his initiation of this. All my many mentors, colleagues and students over 50 years, I can't believe it's that long, I'm greatly indebted to. For the HLA studies, these are the people involved, mostly from my lab, but also Yvonne Jones, who's a fantastically good structural biologist in Oxford. And we've had some usual sort of funding. So thank you very much for the chance to speak here, and thanks again to Stan.
Thanks very much, Andrew. We're moving rapidly towards tea. We're running a little bit late, but if there are any questions from the floor, we'd be happy to take them. Yes, please. Can I have a microphone here, please?
Okay. Thanks. My name's Keith Peters. I'm not a St Mary's graduate, and I didn't work with Stan, but I thought I'd just mention a couple of things. First of all, there's another St Mary's graduate, now sadly died, that's Patrick Sissons, who was greatly influenced by Stan. And as many of you know, Patrick went into infectious disease, became a professor at the Hammersmith, and then came to Cambridge with me and succeeded me as Regius Professor of Physics. And his close associate is Les Borzevich, who greatly influenced by Dieter Askenas also. He was a Cardiff graduate, but he was influenced by Patrick, therefore distantly by Stan, and of course Boris became Vice-Chancellor of Cambridge University. Then 2 other people I want to mention. One is my wife, Pamela Ewan, who was a senior registrar in immunology at the Hammersmith and came to St Mary's as a senior lecturer, succeeding William Franklin and setting up the allergy clinic. Who had set up the allergy clinic. She took over from him in an academic capacity. She can't be here today, but Stan was enormously supportive of her in the field of allergy. And then finally, and personally, I believe it's the case that when I was being considered for the chair of medicine at the Hammersmith, the then dean rang up Stan Peart and asked about his opinions of me versus another very distinguished person, much older than me, actually, Colin Dollery, as it happens. And I was appointed. And then the next important stage in my career, when I was asked if I wanted to go to Cambridge, to the Regis Professorship, I worried about it quite a lot because it didn't seem to be a very good idea at first. And I actually went to see Stan in his office at St Mary's. This was in 1987. Papers everywhere. And he had no hesitation. He said, "You've got to go." So thank you, Stan.
Thank you very much, Keith. I think Colin's name's come up twice today, and it'll probably come up later on this evening. Are there any other questions before we move to tea? All right, well, I'd just like to thank the speakers from this session. We've had a really marvellous session, very, very entertaining, very informative, and I think we'll regroup. We've got time later on. I think we can probably return at 3:25. Right, well, we're moving back towards catching up time, and we've got two really important presentations in this final session. We've heard a lot today about Stan's science, and we've had a lot of remarks from many of the speakers about his mentorship and his teaching, and so I'm delighted to welcome Robert Unwin, who was on the unit in my days and worked in my department for a short period of time, and he's going to talk about Stan the Mentor. Robert.
Well, let me begin by thanking Peter, David, Celia and the Peart family for this opportunity to say something about Stan. You have to forgive me, I have a few notes which I don't usually use, but I have so many things I wanted to cover, I need to remember them. Now, of course, we've heard a lot about Stan as a mentor already today, and I don't think I can do more than try and draw together some aspects, and of course give my own personal view of what it was like to be mentored by him. I think in some ways it may have seemed a rather small part of his life and what he did, but I think it's a very important one, and it showed his kindness, his compassion, and his desire to help all those around him, and sometimes he would give advice to you that you didn't expect or you didn't want. So I think that's a true measure of a mentor, to be able to not just be positive, but to point out the things that may need to change in what you do. But let me just give a few broad words about mentoring and what it might mean, or what people think about it today. So the origins of the term come from the story of Odysseus, who appointed a tutor and guide to his son Telemachus, and the goddess Athena appeared in disguise as mentor and advised him to resist Penelope, his mother's suitors, and acted as his guide and counselor. And it's commonly defined these days as a relationship between two people with the goal of professional and personal development. Of course, the mentor is more experienced and the mentee less so. And it's often said that the ideal mentor is a combination of a coach, a counselor, advisor, guide, role model, and critical friend. And much of what is written about mentorship comes from the business literature, as I'm sure you know, and you can find all sorts of books about mentorship. You can find it on the web, you can find courses, and you will find that many business leaders write about it and often identify it with being a role model as well as being a mentor. But that's a rather formalized structure in my view. What I came across quite recently, which slightly surprised me, is what is known as reverse mentorship, which is where the young mentee actually educates the mentor, and this is very much in the context of IT, with the use of smartphones or introduction to various web methodologies, and the sort of thing that my grandchildren are constantly trying to teach me. So it's really teaching an old dog new tricks. But I think when it comes to medicine, I think medicine always really had an element of mentorship as part of it. It was an integral part, really, of medical training. And I think really what has changed in the last couple of decades is what was, at least at one point, the loss of the clinical firm structure. And I think that was very important because, in a way, that's represented on the left, another picture of Stan, but the old clinical firm, where, of course, you had the lead consultant, you had a registrar or senior registrar, and a junior, an SHO, or a houseman. So it was quite a close-knit group. And I think what I felt, certainly in my experience, was that many consultants who led the firm had a sense of responsibility for their junior staff and their careers, and how they would develop and progress. So there was this sense of responsibility, and I think that was very important. Now, of course, it's true that with that system, there was always an element of chance. You know, I might be very lucky, and you might have worked well for some, but not for everyone. But I think the eventual disappearance of the firm structure and the move to multi-consultant teams, as we have now, and the introduction of shift work, more frequent changeover of junior staff, all put in place for what seemed to be sound clinical and resource reasons, resulted in many trainees, certainly I know that in the case of my own daughter, who was training some years ago now, that she often felt that she was forgotten or neglected, and that no one was really interested in her or in her future careers. And I think she wasn't alone in feeling this. And I think that system made it very difficult for many junior and senior staff to get to know one another and to establish any sort of mentoring relationships. So I do think that's been a problem with the changes. But of course, efforts have been made to address this with the new training reforms and more formal curriculum, more structured professional development, and often an assigned mentor. But an assigned mentor is not quite the same thing, because they can't easily replace it at a more personal level, which depends on personalities, of course, getting to know someone and being fortunate enough to encounter the right person at the right stage in your career. And of course, you need time. You need time with that person. It's not something that you can do on an occasional basis or meet them, once every month or whatever. So I think this was a very important change, and I think Stan's way of mentoring was also facilitated by the older structure. I mean, not to say you can't do it today, but I think it takes a lot more effort and is often very difficult to find the mentor and for the students to feel that they're being supported. But for me, the qualities that he had, I mean, these are fairly typical of a mentor, but for me personally, I felt he was very empathic. He listened. And I always realized that he would never tell you what to do. He would let you talk through your problem. You had to articulate it. You had to put it out there. And you would then come to a sort of solution, or at least you had some idea where you wanted to go. And at that point, he would, in a sense, intervene and say, right, I can help you move in this or that direction. So I felt that was, I mean, to begin with, it was rather disconcerting because you expected him to give you firm advice and this is what you should do next. But I never experienced that with him. He would never tell me what to do. He would listen to what I had to say. And I think that the other thing I found about him, which I'm sure many of others have experienced the same, is that he was very approachable. And I do remember in my early days at St. Mary's, I would often, and I have done so actually throughout my career, contact him unannounced, really, just ring him up or try and drop by and sometimes seeing him at home. But as a junior, I would try to catch him first thing in the morning or late in the evening, particularly when my experiments were going badly or I had some new crisis of confidence, which was quite often, I might say. But he was good about that, because I think it must have been very annoying. I did it rather a lot, but he never showed any annoyance, and he was always very welcome. He would stop what he was doing, ask me to come into his office, ready to reassure and to listen to what I had to say and make suggestions. And I think that was extremely valuable. I don't think he would ever have labelled himself quite as a mentor. But in fact, I think he was, and I'll say a little bit later, there was a particular thing he said to me which made me realize that actually it's a very important activity and something that you have to take very seriously, and it's not a sort of casual encounter with a fellow or a student. He wrote these two articles that some of you may remember in the Lancet. So he wrote one in 1970, which he described as the death of the professor of medicine. And then, rather like Maynard Keynes, when the facts changed, he changed his mind. And in 1983, he said the rebirth of the professor of medicine. And I think to begin with, in 1970, he was very concerned about the super specialization within medicine, what he described as, knowing more and more about less and less. And he was worried that this was going to fragment and make it very difficult to attract people into a career in academic medicine, and it would be very difficult. And then he changed his mind in the sense that he began to believe that it was extremely important, and this comes out actually in both articles, funnily enough, that he really wanted what he described as bridge men, or bridge individuals, who would be able to bring together scientists and clinicians, because it was very important that they worked in parallel, that there wasn't any separation, that clinical activity was all about academic activity and vice versa, in the pursuit of better patient care. And he wanted what he called these bridge men. And I think this was very challenging because, in a way, although he encouraged breadth, it's actually very difficult in today's day and age to maintain high academic standards and activity or in-depth research, and at the same time remain very broad clinically in your thinking and your approach to patients. I mean, I think it's worth trying to do, but you probably have to accept that to some extent you make a little bit of a compromise. But I think, in a way, he was also saying that he thought people who had this quality, who could talk or work in both worlds, as it were, and could communicate, be the interpreters almost, was an extremely important role. And as you can see from the quotations taken from the two papers, and particularly the other one, which I think was something he said in another article, the importance he put in the training of medical students. and how at the same time he wanted structures which gave flexibility, so he was very anxious about people being committed early on in their careers and that they could move across depending on their interests or depending on their talents and aptitudes. That he felt was very important. And as you can see, he really felt that teaching, clinical care and research were absolutely inseparable and needed to be reinforced at every opportunity. And it was about trying to attract younger people into clinical medicine and particularly into academic research. And I think that's come through today, in fact, from many of the examples of those who've spoken. Their own personal experience really, I think, exemplifies how he behaved and how he thought. And as I say, I think these two articles sort of encapsulated his philosophy, which was still there even between 1970 and 1983. But if I say something about my own experience, although I'm not going to say anything about the science, really, that I did with Stan, but I just think it's worth, it's an interesting story, at least I think for myself, and others have said. So I had completed my clinical training and only really done my 2 junior house posts in medicine and surgery, both outside London. And I was sent to see Stan by one of my university tutors, who actually was a neurosurgeon, someone by the name of John Garfield, who had been a student at Mary's in the 1950s and was absolutely convinced that Stan was the person to see, and he certainly revered Stan, and he referred many times to his teaching style, which we've heard about, we'll hear more about from Gordon. But funnily enough, John Garfield actually adopted the same teaching style, as I realized when I saw how Stan taught. And he was quite an interesting person because he was originally a neurologist, but he came to the conclusion that he couldn't do very much for his patients at that time, found it very frustrating. He could make elegant diagnoses, but wasn't able to do much, as he's put it. So he decided to retrain as a surgeon and to become a neurosurgeon. But he was really a physician at heart, and I do remember that very, very well. So he has suggested that I go and see Stan, and I had qualified from outside of London, one of the new medical schools at the time at Southampton University. I didn't really know London very well at all. So with some sort of trepidation, I went up to London. I went to, you've heard, this little cubbyhole that he had on Praed Street, which was next to the renal and metabolic wards, as I remember. And I remember him sitting at his desk, a wooden desk, old wooden desk, in a swivel chair. He seemed to have this swivel chair which sort of moved around, cross-legged with his famous bow tie, and this sort of wry smile, and he welcomed me in. Very easy to talk to. And I remember one particular analogy he gave me, which still sticks in my mind, about clinical medicine and research. And he said it's a bit like a shuffled deck of cards, and that you never quite know what you're going to be handed, but that's all part of the fun and part of the challenge. So I met him just on this one occasion, and by the end of the meeting, he said, well, I think you should apply for a training fellowship. So, and he said, I have a project in mind, and you read it and you think about it, and maybe you could, we'll put it together and you'll make an application. And the essence of the idea, as you've heard already, was his interest at the time, which was this idea of the control of sodium excretion in response to changes in diet, particularly in dietary sodium. And he had this idea that there was a sensing mechanism, but more than that, he was interested in what the effector might be. What is it that might actually deliver the change in renal function? And at the time, there was a lot of work being done on the new gut peptides by Stephen Bloom at the Hammersmith, who's measuring many of these. And nobody really knew much about their actions other than their relationship to kidney function, and there was, to gut function, and also some endocrine aspects. But no one really had any knowledge of what they might be doing for the kidney. So the essence of the study was to explore a number of these gut peptides and their function and effects on the kidney. So I put in this application and modified it a little bit and discussed it with him, and went for the interview, and I got it. I was ordered the fellowship. I was pretty surprised because I really had only done one SHO position since that time. I just got the membership, but that was it really. I had no reason for anyone to think that I would have any aptitude for research. And when I told him, I just remember he smiled and he laughed slightly and he said, "I should hope so," when I was awarded it. So I then joined the medical unit and spent a good many years there to begin with, doing the this project, which became a PhD. And I met, of course, many of the people spoken today. I actually shared an office with David Gordon for a short while. And I think I was well supported. It was a very good environment. I mean, I didn't know anything else in a way, but in retrospect, I can see that it was a very supportive and enjoyable environment. But then I had to, when I finished my PhD, I had to go back and do clinical training. And I do remember that I was quite anxious about that. But Stan's view was that actually it didn't matter too much. He said, you know, if you've got the intelligence, he said, you know, you'll pick up anything that you need to pick up in the time, you know, so don't worry about that, so return. But I didn't know where to go, and at the time he was making suggestions to visit various units around the country. By then I decided I was interested either in general medicine or possibly nephrology, but I hadn't really thought of it that strongly, so he made some general suggestions, but it wasn't really very appealing to me. And then suddenly a position came up. I was just talking about this at St Mary's, to the extent that the interview was on the day that it sort of came up, and he offered to provide me his jacket so that I could actually attend the interview. So I got the job, perhaps not a surprise, and was there did a beginning of a rotation, then got back into the medical unit, first actually with Peter and then back with Stan. So I was able to continue my clinical training and to continue my research. But I got then much more interested in the kidney, and so he said, right, well, the next thing you need to do is you've got to go a bit further. You've got a very sort of superficial knowledge of the kidney and overall kidney function, but you don't really have any understanding of how the kidney works at the single nephron level, you know, at the cellular level. So he decided to send me off to Gerhard Giebisch in Yale for 3 years, which I did on a welcome fellowship. In fact, Chris Wilcox had been there before me, so that was quite good. And that was a very interesting time, very difficult time. It was pure physiology for 3 years in a very interesting laboratory, and I was taught a lot, learned a lot of my renal physiology, which I found extremely interesting, and mastered this difficult technique of tubule single nephron micropuncture, which was very challenging, I might say. And then I returned to the UK. Again, I wasn't sure what I was going to do clinically. You know, I was really my training had only been in general medicine, no specialty training to speak of. I then had a short period at the Hammersmith in clinical pharmacology that was more closely allied, and I realized at that point that it was nephrology or renal medicine that was really the way to go. Otherwise, I couldn't combine my research interests with my clinical interests. But I had, you know, how could I do this? I was pretty late in my career to suddenly become a trained nephrologist, which is something almost impossible to do today, to actually take up a specialty when you're already in your middle 30s. But in fact, again, with Stan's support, when he knew that's what I wanted to do, Guy Neild, who was at that time just been appointed professor of nephrology at the Middlesex in London, said, oh yes, I'm interested, I'm very willing to take Robert on, which he did, took me on. And essentially he trained me really as a very old postgraduate, as we heard perhaps a little earlier about going back and doing a lot of the basic training in nephrology already as a fairly senior level, but at least I could continue some of my research. And the other important thing that was a result of this was the contact with Oliver Wrong, which was also indirectly supported and helped by Stan. And that really got me into my main area of interest, which is tubular physiology, and the fact that I could link that with clinical interest because of Oliver's interest in renal stone disease, nephrocalcinosis. He also was interested in many of these, at the time, what were considered rare tubular diseases with problems with salt and water, which eventually were shown to be genetic, and did some early genetic work with Oliver looking at one particular form of tubular disease where we eventually identified the gene that was responsible for this, and that opened up the field, and it fitted in very nicely with what we understood of physiology. So I suppose what I've been trying to say in all this is that I think Stan was really, I think curiosity drove him more than anything, and I think he was curious not just about people and those around him, but he was always coming up with ideas and thoughts and problems, things that he'd seen, he'd read, a patient he'd encountered. And that's something that I'll take away with me. And it could be a bit of a problem, perhaps, because it keeps you rather diffuse and broad. And I think if I consider one failing in myself, which probably didn't quite follow what Stan would have recommended, while he was interested in being general in many ways and being broad, you had to have single questions or specific questions. And I think I tended to become rather too broad, probably in an effort to follow his line, but in the current state of things that proved to be difficult to do. And so I probably dabbled a little more than I should have done, but at the same time I found that very rewarding, and after all he was quite eclectic, I think, in his interests, so I would never consider that a weakness. But one thing he did say to me, that he said that any career in medicine, particularly as an academic, you have an important responsibility that takes a lot of time, and that's the mentoring, the support of young fellows. He said it's not something, it requires quite a lot of effort, and there's time. If people can just knock on your door, drop in, talk to you, or come to you, you have to be open to that, and that will take time. But at the same time, it's very interesting usually, and either they bring a new problem, a new clinical problem, or a new scientific problem, or their own sort of problem. Again, that's about being curious, I suppose. But it's quite a rewarding distraction in some ways to do it properly. So what I'd like to do is just end with some quotations which I think fit Stan rather well. I mean, I think it's true you do want somebody in your life who will make you do what you can. And I think for me he was someone like that. His teaching was very much this: tell me and I forget, teach me and I may remember, but if you involve me, I will actually learn. I'll get it, I'll do it. And the one I like from Bertrand Russell really is the hardest thing in life is to know which bridge to cross and which one to burn. And that's where you need someone to help you, because no choice is necessarily a bad choice, but you have to make a choice at some point. And I think the last thing, which I always felt he would say about himself to some extent, I think, that no one should believe himself to be perfect, and you shouldn't worry too much if you're not. So I would say thank you, Stan. Thank you, everyone.
Thank you, Robert. Thank you. And now for the last formal presentation, I'm going to ask Gordon to come back and talk to us about teacher and clinician.
Thank you. Thank you. I'm back with a glass of water this time. No slides. This is going to be short. So we've heard today about Stan's astuteness as a physician, and no one has had any doubts about that. No one who worked with him can have had any doubts about that. And the nurses and the patients all admired him very much for all that. So I'm not going to say any more about that. Now, about the teaching, Professor Townsend described the sessions that Stan used to have. It was just once a week in my day, but he used to get us as juniors to identify a patient, and then we'd get the patient along to the small lecture theatre, and then Stan would go through the patient blind, not knowing anything about the patient's background, and eventually come up with a diagnosis. Anyway, on one particular occasion, we did this on the ward round. So I was the houseman, and Professor Terry Cook down there, I was the registrar, and Professor Cook down there was the houseman on the firm at the time. And we had admitted this young man. He was in his early 20s, and he'd taken an overdose. But it was all rather unique because he'd taken an overdose of a treatment called penicillamine, not penicillin, but penicillamine. And he had a condition called Wilson's disease. So for the non-clinicians, this is the disease, an inherited disease in which the body accumulates too much copper, and it affects many organs, but the main organs that it affects are the brain and the liver. And penicillamine, it was the first really effective oral treatment for this, introduced by Dr. Walsh in Edinburgh. And the young man had had a difficult time with his parents, and he had been cast adrift, really, and he was on the streets, and he was being bullied by yobs. And he took an overdose of his penicillamine to escape. And he came into the ward. And we had him, as I think I remember, on the second bed on the left in Albert Ward. And we were doing the Friday afternoon ward rounds. And the other thing that was special about this occasion is that we had these two visiting students, medical students from Stanford, bright young men from North America. And I thought it would be interesting if we just said to Professor Peart that this young man has taken an overdose. And we left it at that. And I implied to him that he had to get on with it now. And he gave me a look. I can still see him giving me a look. But anyway, he turned his attention to the patient who was lying there on the bed, and he had some obvious neurology from the bottom of the bed. We had no history, and Stan took to examining the young men, and the Americans were surprised at this approach to the ward round. It was 3:30 on a Friday afternoon, but as we all knew, we had the whole afternoon and the whole evening to get through all this. Stan's ward rounds being characteristic for their duration and their timing, as we remember. Dr. Thomas used to remind us about that. Now, so he started, and the young man opened his pajamas, and he had a scar in his left hypochondrium here. And we looked at the pulse and the chest, and then we got down to, which were normal, and then we got down to the scar. And he started talking about the scar, and the two Americans then began to hear all about it. And why did he have this scar? And what was going on here? And isn't this unusual? And why might he have this? And we got down to the idea that he might have had his spleen removed through this scar. And why would a young man have had his spleen removed, etc., etc., etc. We went round the splenic houses for 20 minutes or so while we went into this. And we eventually came to the conclusion that he might have had something the matter with his liver. It's possible, isn't it? And then we got down to the neurology, and we went through all the parts of the neurological examination, and the young man's speech was not quite right, and he had abnormal movements of his hands, and Stan went into all the ins and outs of all these neurological signs. And then he started doing the reflexes, and he found that you remember this, Terry, that the deep tendon reflexes were increased, and that he had upper motor neuron signs. So at which point Terry and I retreated to the back and, does this happen in Wilson's disease? We didn't know, and we weren't expecting it. So we learned something during this session too. And so we went into the physical signs with these two Americans, with us listening in the background. And we came to the definite conclusion that this young man had Wilson's disease, which was, of course, absolutely correct. So here was this consultant in London diagnosing Wilson's disease purely from the physical signs. He's not a neurologist, he's not a hepatologist, he just knows everything. And it was a very impressive sight. And the Americans were just stunned. They had never seen anything like this. Well, neither had we, basically. And it was a very instructive thing. And I'm sure they, like Terry and I, they have never forgotten that particular occasion. And if there's one thing that marks you down as a good teacher, is that you can have a session which is never, ever forgotten by the students that you took. That doesn't happen very often, I have to say. Anyway, that was him as a combined clinician and teacher. And, you know, every week was a bit like that. And that's what made him so great. Okay, that's all. Thanks.
Yes, you're right, Gordon. You could never catch him out, could you? God, we tried week after week after week, and you never caught him out. There's just one other thing I will say about Stan as a clinician, and I think he's the only person that I've ever heard say it. And if you're interested in the story, if you go onto the internet and dial in Stanley Peart, there are 6 hours worth of interviews of his life as a scientist, a clinician, and a teacher. And I would commend it to all of you. It's absolutely fascinating. But the thing that he taught me, and that I think was the most memorable thing about his clinical approach to patients, was the following. He would say, the most important thing that you should ask a patient who walks through the door into your office is, what is it that is ailing you? What is it that you are complaining of? And the reason he said that is that in the increasing era of specialization, you will have patients referred to you for your gastroenterology advice. You'll have patients referred to the chest physician. You'll have patients referred to the cardiologist. The patients arrive with all their investigations that have been done before they see you. And there is an assumption that what you as a clinician are going to be dealing with is something within that speciality. But that was not Stan's approach. Stan's approach was to find out from the patient what it was that they were particularly complaining of. And that was frequently not mentioned in the letter of referral. A really, really important message. And every medical student today needs to be taught that that is the first question you should ask. Well, I hope, ladies and gentlemen, the Peart family, you've enjoyed today. David and I have had a marvellous time putting everything together, and we're delighted that so many of you were able to join us. And I now, it's a great pleasure to ask Bridget Ogilvie to give the closing remarks. Bridget.
Well, it is, of course, a very great pleasure to be able to talk about Stan in this capacity, of course, as a governor of the Wellcome Trust. And I think this is entirely appropriate, as it's quite obvious from the talk today, how many of you benefited from the Wellcome Trust, not necessarily always when Stan was there. Now, I was a member of the staff of the Wellcome Trust for 19 years, ultimately as the director. And I know that Stan was heavily involved in deciding that I would be promoted to director. And to illustrate once again his breadth of knowledge and understanding, this despite the fact that my first degree was in agriculture. I'm not medical. Now, Stan was in many ways the outstanding, the most memorable of all the scientific governors during my time at the Wellcome Trust. It won't surprise you. And one of the reasons he was so important and so successful was because he never, as Roger Gibbs, the chair at the time, said, sold his own book, i.e. promoted his own interests well above everybody else's, which was not necessarily a characteristic of all the governors of the Wellcome Trust. He set up various programs, special programs, to strengthen research in disciplines which he thought were suffering from having insufficient research: psychiatry, clinical infectious diseases, clinical epidemiology, and ophthalmology. He also, of course, chaired the committee making senior clinical fellowships, which, of course, is the longest-standing Wellcome Trust scheme, which set up by Andrew McMichael's father, actually, originally. And very often he would insist that the recipient of these fellowships had spent 2 years developing their strength in research, a theme which has been repeated over and over again today. Sometimes these people didn't like this. Very often he'd say, well, I think you should go to the States to such and such a place, and of course at Wellcome Trust's expense. And I remember having to tell one individual, now very distinguished here, that this was the condition on which he would get this fellowship. He'd have to go to the States. And this guy was furious. But eventually, after he came back, he came in to apologize to me, to say, and to tell Stan how right he was. So the other thing that I particularly remember, we had a small scheme of fellowships in Australia and New Zealand at that time. And the aim of these was to bring back to Australia and New Zealand citizens who will be distinguishing themselves in science or medicine abroad. And we were in New Zealand interviewing for this at one time, and afterwards we decided we'd walk the Milford track. And Peg was there too, in the very early stages of her unfortunate Alzheimer's. And the Milford track is a 3-day walk in an area of the world that has 270 inches of rain a year. And so most of the 2 of the 3 days were very wet. And Stan put his boots at the end of the first day of rain rather too close to the fire. And the next day, when he had to walk 13 miles in the pouring rain, flap, 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 his soles of the boots were almost off. And here he was, helping Peg as he went along and flapping through the rain to Milford Sound. So that was very important. Now, the other thing that I really appreciated, at one time, 4 of the 7 governors of the Wellcome Trust were Oxford people, so I was always extremely glad that Stan was not an Oxford man. And we worked together to devise ways of encouraging people in Edinburgh, Manchester, Leeds, even London, to apply for grants to the Wellcome Trust, because we were over-indulging Oxford on a huge scale at that time. So that was a very important thing. Now, he was such fun, and as you've already noticed, completely free of self-importance. And he seemed to be very interested in birds, because very often when he was talking about somebody's particular habits, he'd say about somebody who was highly territorial, oh, it's his robin instincts, or her robin instincts. And frequently he would say to me, everybody needs a monitor bird. That's a bird that sits on your shoulder and shouts in your ear, rubbish, rubbish, at frequent intervals. I was never quite sure why he would say that to me. But anyway, I've never forgotten, of course. So in sum then, Stan was an absolutely exemplary governor, and in the eyes of many of us at the Trust, a very great man. And I think this simply reflects something that has been said frequently today. So thank you all.
Well, ladies and gentlemen, that's it. I think we've had a wonderful day. And Celia, do you wish to say something now?
I just wanted to say a few impromptu words of thanks.
Of course. Okay? Of course, yes. Please do.
Well, on behalf of all our family, I'd like to thank everybody involved in all the hard work that went to putting this together. Ian Walmsley for the welcome, Bridget for your closing remarks, the Imperial College team for putting the event together, and especially for Katie, who couldn't be with us, Peter and David. Wow. Your perseverance and your kindness. I really appreciate. I just wanted to add a couple of things to this very comprehensive tribute to our father. One was going back to the penicillin ward. That was actually where my parents met each other. And my father, though he was quite dashing. He was also quite shy. And my mother was the staff nurse on that ward. And my father's chat-up line apparently was, "Can I borrow your scissors?" And the rest is history. But I don't think my father could have had the career he had or any family life without my mother's support. And the second thing I wanted to say was on the debate about sodium intake. My father broke his nose quite badly playing rugby, so he really had no sense of smell or taste as time went on. And as his memory faded and his kidney function also was failing after his heart attack, he became very, very fond of salt, and he liberally applied it to every dish. And in fact, we had to prevent him from emptying the entire salt cellar onto his plate of food. So anyway, thanks again. I've really learned, I think we've all really learned a lot, our family. We didn't realise how many fingers he had in so many pies, and it's been very moving for us all, I think. So we thought we'd end up with a musical interlude before we all head off for a well-deserved drink. And while it's not seasonally appropriate, I know that my father would heartily endorse and loved, actually, Tom Lehrer's Poisoning Pigeons in the Park. So thank you very much.
Sorry?
We were supposed to get a YouTube clip of that, so I don't know whether it's happened or not.
Do we have the clip of that? I can't see anything from the box upstairs. We'll just give them a couple of moments to see whether we can find that. I'm interested in that last comment about Stan shoveling salt on his food. He must have got that from George Pickering, because that's precisely what George always used to do, because he never believed salt had got anything to do with hypertension. Anyhow, ladies and gentlemen, I hope you've enjoyed today. As I said earlier on, David and I had a really marvellous time putting everything together. We shared several excellent lunches at various established restaurants around London, so it was mostly enjoyment for us. And thank you, all of you, for coming. Thank you for all the speakers for your marvellous presentations. And now I think if we haven't, unfortunately, got the YouTube clip, it's probably time for some refreshment. Many thanks.
spring is here, spring is here. Life is skittles and life is beer. I think the loveliest time of the year is the spring. I do, don't you? Of course you do. But there's one thing that makes spring complete for me, and makes every Sunday a treat for me. All the world seems in tune on a spring afternoon when we're poisoning pigeons in the park. Every Sunday you'll see my sweetheart and me as we poison the pigeons in the park. When they see us coming, the birdies all try and hide, but they still go for peanuts when coated with a cyanide. The sun's shining bright, everything seems all right when we're poisoning pigeons in the park. We've gained notoriety and caused much anxiety in the Audubon Society with our games. They call it impiety and lack of propriety and quite a variety of unpleasant names. But it's not against any religion to want to dispose of a pigeon. So if Sunday you're free, why don't you come with me and we'll poison the pigeons in the park? And maybe we'll do in a squirrel or two while we're poisoning pigeons in the park. We'll murder them all amid laughter and merriment, except for the few we take home to experiment. My pulse will be quickening with each drop of strychnine we feed to a pigeon. It just takes a smidgen to poison a pigeon in the park.